Sunita, I'm just setting up the live. Give me a minute or so.
Okay.
Yeah, live setup.
It is up, yeah.
Yeah.
So Bibu is also here. Will be the chairperson for the coming session.
Yeah. Hi, Sunita. Hi, Partha. Hi, Bibu. Raining heavily here, so hopefully I will still get connected sometimes.
So how is the situation in IIT now? The students are back?
Asking me, Sunita?
Yeah.
Yes, students are back for the experiments, not for the real classes. Classes are still online.
Okay, so the undergrads are still online.
But then we got them, the final year students, for the experiments, and even the first year and other year students for the lab classes. They are physically, they have to do the lab classes.
So that will happen after the teaching is over or something like that?
No, they are already, some of them are already here. We are getting batch by batch. So the master students we finished just last month. Now it's the undergrads that are going on.
Hopefully we'll be able to have physical classes from next semester.
Yeah, I so badly miss them. Online teaching is.
Yeah.
So Bibu, you are based out of? Sorry, I saw so many names I cannot recollect the affiliations.
So I am from IIT Palakkad. IIT Palakkad.
Palakkad, okay.
Yes. It's a new IIT.
Yeah.
The 3G IITs, yeah.
Yeah, I have gone as far as IIT Tirupati. So.
Yes.
No, it's the ISO Tirupati. Sorry, that's the farthest I've gone. IIT. So you are in chemical engineering or chemistry?
No, I'm in physics.
Oh, you're in physics. Okay.
Yes.
I used to be in physics. So
Bibu, me and Parto are actually batchmates from our MSc time.
Oh, okay.
Yeah.
Pune, is it?
Pune, yeah.
Yes,
so
yes.
We did our
and
masters.
With Bibu, we had an overlap in Bangalore during our PhD.
PhD. Okay. Yeah, I used to be in physics, and my research area was, so when I was doing my PhD, still physicists were interested in it. But by the time I graduated, chemists picked up that area, molecular electronics. So I did all my postdocs in chemistry department, and that's how I drifted into more of physical chemistry. And landed up with a chemistry journal.
Experimental or
No, computational.
Calculations, right?
DFT calculations, yeah.
Okay.
I have no experience with instruments, zero. My only experience was in masters. I did some field emission experiments, but that too for namesake. I used to just turn a knob and take some measurement. That's it.
Okay. So Danny, should we start now?
Yeah, everything is set.
Yeah. So Bibu, maybe you can formally introduce.
Yeah. Okay.
Yeah.
So good afternoon all. Welcome to this afternoon session of this e-SMYIM. So the most important aspect of research is probably publishing your data, and it is always good to have a perspective from the insider view or the perspective from the editorial process. I mean, how it happens there, and who else can be more appropriate than the associate editor himself So we have Partha Pratim Pal from Wiley, who is associate editor in Wiley. So just a brief introduction about him. I think he did his master's in University of Pune, and then he went on to do his PhD in Michigan Technological University, further postdocs from University of Michigan, Northwestern, and Pennsylvania. So his primary research area is on computational research on molecular electronics and electronic structures of materials. But today he is going to talk about the insider view of the editorial process for a manuscript substituting. So Partha, the stage is yours.
Thank you, Vibhu, for the nice and kind introduction. So just can you please confirm that you are able to see my screen?
Yes.
Okay, and the full screen, right?
Yes, it's all good.
Okay, because I cannot see anyone now. So hi, hello everyone. I'm Partho. So right now I'm a associate editor with Wiley. I joined in 2019. The outline of my talk today will be, I'll start with some introductions, the company John Wiley and Sons, my team, the editorial office, the chemical societies we work with, and our role. And then I will briefly talk about some of the Wiley journals which I think is relevant to this community. And then the first part I will close by talking a bit about open access and predatory journals, which are creating a lot of nuisance these days. And then I'll pause a bit if anyone has questions, and then I will move into insights and tips. Like as editor, what we look forward to in a manuscript and things like that. I'll describe the review process briefly, although most of you are aware of it. And then finally, I'll conclude with the other activities we as editors perform other than handling manuscripts. So this is my journey to Wiley. I did my bachelor's and master's here in India. Did my master's in University of Pune. I was a batchmate of Sunita, so we did our master's together in physics. And then I was working in computational molecular electronics. So by the time I graduated, most of the chemists were interested in it. So I did my postdocs in chemistry departments, and that's how I shifted more into physical chemistry. These are some of the papers I published. As you can see, most of them are from the ACS journals and a couple of them from the American Institute of Physics and APS journals. So briefly, just for the sake of completeness, I will talk about the parent company, John Wiley and Sons. We have this Wiley online library, which most of you are, or all of you are aware of. We have about 1,600 plus journals, 21,000 plus books, and about 18 million visitors each month. Wiley is also the founding publisher of Research for Life that provides free or low-cost access to more than 1,200 Wiley journals in 90 developing countries. So a big chunk of the chemistry editorial team is actually based out of Weinheim. You can see the red dot here. It's about 45 minutes from Frankfurt. There are about 400 employees there, and most of them have done their PhDs and postdocs like me, and now they work on different journals. So this is how the office looks like. This is where I was trained. Different desks for different journals. It's a huge room, and these are the names of the journals associated with the desks. So our India office opened sometime around late 2018, and I started early 2019. We have currently 2 in-house editors, myself and Khushbu, who is based out of Delhi, and 3 commissioning editors who do not handle manuscripts, but overall manage some of the journals in their portfolio. Okay, so a bit about the editorial models. So our model internal is us. So we have the editorial office. Okay, so let me just explain this purple thing. The purple circle means it's a practicing scientist, so professors like you. So the journals have the editorial board, which consists of faculty members and also the advisory board. Same thing. Then there is the editorial office, which is actually associated with the publisher. So that's the two blue circles. So publisher is like Elsevier, Wiley, and then there are the societies, societies like the American Chemical Society, then the Royal Society of Chemistry, then there is the Chemistry Europe I briefly talk about. So this is one model, and myself and Khushbu, we are in this model. And then there is the external model where the editorial office is actually in a academic institute. So the editorial office and the editorial board are in the same place, and the publisher sits in a different place. And then again, there are the societies. Now, both these models have their own advantages and disadvantages, but we are not going into that. I'm just going to say that we are associated with this kind of a model. Now, our role is actually an art of balancing. So these are the different stakeholders you can see here. The readers, they want quality manuscripts to read, which has undergone rigorous peer review, and they don't want any ethical issues or disputes. The reviewers like you do have time constraints because this is not your primary job. So they do want us to be flexible with the amount of time they're given for their reviewing duties. For authors, decision times matter a lot. Everybody wants a fast decision. They want a fair process, and then they want a quality, so which is the visibility and citation matrix. And also they want the editors to be they want the editors to be friendly and the process to be friendly, which means the interface they use to submit the manuscripts, they should be user friendly. The societies which are associated with the journals, they would want to get something out of it, so that the royalties, they look forward to it, and they want value for their members and also the reputation. And finally, the publisher, of course, they would take care of the costs and look for profits and the market share. The societies we work with, you must have all heard about Angewandte Chemie. So this is a journal belonging to the German Chemical Society. It is based out of Frankfurt. It is published by Wiley VCH, which is based out of Weinheim. And Wiley VCH is a subsidiary of John Wiley and Sons, which is the headquarters is in Hoboken, US. Then there is the other society, Chemistry Europe, which has 16 chemical societies from 15 European countries, and and we have 17 journals with them. Then there is the Asian Chemical Editorial Society. So CRSI, Chemical Research Society of India, is one of the founding members of the Asian Chemical Asian Chemical Editorial Society. And CRSI actually receives royalty if Indian authors publish with the ACES journal, and they can use that royalty for any CRSI activities. The flagship journal of the Asian Chemical Editorial Society is the Chemistry and Asian Journal. So some of the activities we have done recently is we celebrated the 20th anniversary of the CRSI. Professor Shantanu Bhattacharya gave a lecture on the 25th CRSI National Symposium. That was back 2 years back. We had a special issue on 20th anniversary. The guest editors were Professor Mukesh and Professor Sandeep Verma. We have various board members from India. As you can see, almost all the premier research institutes in India are covered, and they're associated with the various journals in various capacities. Recently, we have started the early career board members. So this is basically early career researchers who started their independent careers within like 5 or 6 years. So most of them are assistant professors. And then we are looking forward to add more this year. A couple of projects I would like to mention we have done. or are doing. So right now we are doing a special collection on the 15 years of since the inception of ICER, which is the ICER Kolkata and ICER Pune. They're celebrating their 15th year this year. We are having a special collection. We did a special collection on IIT Bombay last year. Then there was this conference on organometallics and catalysis. We did a special collection on that conference. So now something about the peer review process. How does it work and where we come in? Editors like me and Kushbu, where we come in. So as an author, you submit the manuscript to our journals. We examine it and make an initial decision. So that is the desk. We call it a desk decision or something like that. So if we decide that it is not suitable for the journal in one way or the other, we would reject it. So that would be the desk rejection, or we would offer a transfer to a different journal. And sometimes if the format is too bad, or if the graphics is too bad, or the language is too bad that it is preventing the reader from understanding the science, we send it back to improve and polish those things and resubmit it to us. If the manuscript looks good to us, we send it for peer review. Then we make a decision based on the referee reports. And the decisions can be acceptance with minor revisions, and finally it is accepted and it goes to the technical department for the final formatting thing. If the decision is rejection based out of the report, so in that case we sometimes, most of the times, we actually try to give offer a transfer to a different journal. Sometimes if the referee asks for a lot of revisions, we reject it, but then we re-invite the author to submit a revised version. And then again, we go through the revised version, and sometimes the revised version is accepted right away. So as you can see, in all these areas, this is where we play a role, we as professional editors. The next topic I'm going to briefly talk about is how to choose a journal. There are various factors which come into place when you are choosing a journal. The first and foremost, we think, is the target audience. And I'll show you in a minute why target audience is very, very important. Now, this picture here basically shows that it's a multi-lane road. And how do you decide which lane to take? So it depends on your destination, right? So in this case, the target audience is the destination. You can look at the literature from the bibliography of your paper, and then that will help you choose some of the journals. Then you go ahead with, you can make a choice of like 4 or 5 journals, and for each journals you can check their scopes, the types of article they publish, what are their other requirements, and also definitely the impact factor. Now I will come to the point as to why the target audience is most important. This was published 2 to 3, maybe 4 years back. So he is a practicing scientist, Jason Dutton, La Trobe University in Australia. So this is a quick summary of the number of sites per year, as you can see here, and 2016 journal impact factors. And as you can see, that publishing in a higher impact factor doesn't actually guarantee you more number of citations per year. So 2 to 6 are like mid-level impact factors, but those papers are cited much more, as you can see here, than the ones he published in very high impact journals. So high impact doesn't mean publishing in a high impact journal doesn't guarantee you more number of citations. Next, I will briefly talk about some of the journals which I think you might be interested in. There is the advanced flagship journals. These are predominantly materials journals. The advanced materials, advanced functional materials. Then there is small, then the advanced energy materials, and then there is the fully open access advanced science. In the chemistry portfolio, we also have some energy and materials journals. Like we have the Chem Nanomat, which is one of the ACES, the Asian Chemical Editorial Society journals. For the chemistry Europe, we have the batteries and supercapacitors. Then there is the macromolecular molecules and engineering. And then there is the PSS Babe, which is more of a physics journal. Some of the physical and inorganic chemistry journals you might be interested in are ChemPhysChem, UCHIC, European Journal of Inorganic Chemistry, ChemElectrochem, and ChemPhotochem. On a daily basis, I work with these two journals, ChemPhysChem and ChemElectrochem, and also with Chemistry Select, which is also a can say a general chemistry or a multidisciplinary journal. Chem Plus Chem is a heavily multidisciplinary journal. So as you can see from the name, it's two disciplines of chemistry involved in the research. So that would be Chem Plus Chem. And Chemistry Open is a fully open access journal. So our top general chemistry journals are Angewandte Chemie, Chemistry, a European journal, the flagship journal of Chemistry Europe, Chemistry and Asian journal, the flagship journal of ACES. So for enhancing the accessibility of these journals, we do have these mobile apps. I will now briefly touch upon the subject of what is open research. So the open research is actually driven by the European Commission. Basically what it says is open science or research is the ongoing transition in how research is performed and knowledge is shared. And open research is supposed to make science more efficient and accessible to the to everyone. So what are the key drivers to open research? Digital technology that enables collaboration and dissemination. Also, there has been some amount of criticism of how the traditional peer review models work. Then there is the growing public scrutiny of what researchers are doing with, as you know, most of the grants are basically taxpayers' money. So the general public demands that they would like to know what is being done with their money. Then there is the changes to research assessment matrix, including the emergence of altimetric, and the pressure from funders to make their funded research more accessible and impactful. And also, more and more researchers are actually looking to reproduce the results that are published in the literature and verify them. So what are the benefits of open research? Increased openness makes the process more transparent and accessible for researchers, increasing reproducibility and increasing accountability. So how is Wiley supporting open access? We have this green open access self-archiving. What does it mean? It means the author, institution, or the publisher places a version of the article in a repository or website after 12 months after publishing in a subscription journal. Then we have this gold open access, which is like the author or the institution or the funder typically pays the article publication charge, and then it becomes free for everyone to read. And then we have this translational agreements, and it started with Germany. So the funding agencies have an agreement with Wiley that they are going to pay the article publication charge, but we will have to make the article open access. Okay, so open practices, we have this Publons and ORCID that recognizes the work of Wiley peer reviewers. And we are also supporting the preprint policy. So that actively supports openness and allows researchers to publish their work on a preprint server. So the oldest one is the archive, and now there is the Chem archive, there is the bioRxiv also. Okay, then I would like to talk briefly about the predatory journals. It's a shady world, and you should be very careful while choosing a journal, and preferably if you do not get a lot of information about the journals, probably it's not the best idea to publish there. So basically the predatory journals, as you can see, I'll show you an example. So I've made some statements here, and then afterwards I'll show you an example. The editorial staff and editorial board members, they are not identified, so no academic qualification or affiliations are given. There is a lack of transparency in the publishing operations. The publisher doesn't allow the search engines to find the articles. Then there is just a empty claim of community standing, impact factor, those things. But if you do a deeper search, you won't find anything. Spam emails. This is the most common way they would like to catch the attention of authors to submit papers to their journals, and those emails usually have terrible spelling errors or grammatical errors. And the publisher makes little or no effort to make the content discoverable. And sometimes it even steals the name and web contents of a similar journals. So here is a nice example of identity theft by a predatory journal. I would pause here briefly if anyone has any questions. Otherwise, so basically for you, can you guess which one is a predatory journal and which one is actually the original journal? So one is this, one is this. I'll pause for a few seconds, and if you have any questions, I'll be happy to answer them now. And then I'll move on to the next part.
Yes, if anyone has any question, please kindly unmute and ask directly.
So I had a question about resubmission of a manuscript that you talked about briefly. So when author resubmits, then it goes for a new review process, or it goes to the same reviewer back and it is reviewed again?
So in most cases, we send it back to the same reviewer because the reviewer had already read the manuscript and made an assessment. Unless if the reviewer is not present at that point and the editor is not an expert in the area to make an assessment by reading the reviews revised manuscript, in that cases in those cases only we try to find a new reviewer. Sometimes even we reach out to our board member to say that this is a revised manuscript, and if you can please look at the comments, the response to the reviewer comments, and give us your assessment whether the author has responded appropriately to those comments or not. So yes, to answer your question, most of the times it goes back to the old reviewer, unless the previous reviewer is for some reason very angry and it is very obvious that they won't like to review the paper once again.
So that's also the situation when you have re-invited the authors after rejection. That's the
Yes.
Okay.
So the re-invite is usually in those cases where the reviewer asks the author to do a lot of revisions. In those cases, we reject and ask the authors to resubmit.
Okay, thank you.
Sure.
Shobana?
Yes. Hello, Dr. Paul. I have one question. First question is, why are reviewers not paid for reviewing the manuscript? I mean, is there any reason for it?
There is. Okay, this is a very difficult question. It's basically traditionally it is considered to be a voluntary work, and it has always been like that. I am not aware of any publishing house or society paying the reviewers for their work. So it is like you also publish, so your work someone reviews, and then when that person submits their paper, you review it, so kind of cancels out.
Okay. 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 Okay.
So probably that was the idea. But
Probably.
yeah,
Who knows? Okay.
yeah.
Yeah. Okay. Okay. My next question is, this open access. Now, many journals charge so much money. Like, for example, one like Nature Communication charges like $5,000 for one paper in open access, or Cell, or even Wiley Papers or RSC.
Yes,
If they have
yes,
open app, they charge like a fortune of money. And
yes.
I'm just interested to know where that money goes. Because if the reviewers are not getting paid and the rest of the journal and publisher activities have been going on like they have been for many years. So where is this? Because this is also kind of government and stakeholders' money.
Yes. So to answer your question, see, there are two types of journals. One is the subscription journal. So the author doesn't need to pay to publish, but the reader has to pay to read it. Okay.
Right.
Then there is this open access journals where the author has to pay to publish it, but the reader doesn't have to pay because it's open access. Anyone can read it. So in a way, somebody has to pay. It's the author or the reader. Now, there is a controversy like which is better. We don't know which is better, but somebody has to pay because us editors, we are paid employees. So one part is that. Then there is the cost for archiving the articles so that it is accessible to everyone for the rest of their lives, right? So that involves a cost. So that cost is either acquired from the subscription or the article publishing charges, the APC charges. Does that make sense?
Yeah, it makes sense. Just one last question. Of course,
Sure.
everything you said is wonderful. When you said about open access, that it's open to the society and,
Yes.
So my question is that then why not make it free? I mean, if that is the bigger goal to serve the society and, make the information reachable to everyone, then why charge that much of money per article? Because I mean, you can imagine if one article, solicits like $5,000, and there are like, I don't know, 40, 50 articles in one issue, it's like a huge amount of money.
Yes. So if the article publication charges are zero and it is open for everyone to read, then practically no one is paying money to publish, but it requires a cost to archive the article so that it is accessible to everyone. So somewhere, so nowadays it's in this arena of cloud, it is stored somewhere, right? So there is a maintenance cost involved in that, right? So that is there. And then there is Nature and then Wiley. We have this set of professional editors.
Right.
So with that amount, our salary is paid and the cost of archiving is absorbed. So that is my point. Now, your point of why this amount is huge. Okay, I'm not a finance person, so I don't know exactly why this is so much and why it varies a lot with different publishing houses. But all I can tell you is a simple thing. When you publish an article and in an open access journal, you pay the price once, okay? $5,000, let's say. You pay it once for lifetime, and then you pay it once and it is accessible to everyone for lifetime, okay? But for the subscription journals, the subscription is renewed every year or every 2 years, whatever be it, right? So there is a regular, I mean, it's not one time. Every year the money is charged. So I think maybe because of that, the article processing charges, they sound quite high. And for the subscription journals, usually it is taken care by the institutes. So for the authors, it is, I mean,
free.
You don't know how, so it is free.
Yeah,
So
it's on the order of a few crores. I know that. Yeah.
Yes, yes. So, but then it is done every year, not like
Right,
once,
right,
right?
right.
So maybe because of that. But again, I'm not the right person to talk about this one.
Okay. Well, I just hope that with the invent of, open access, which has, I think so, last 5 or 10 years, or maybe 5 years, it has come up. So I hope
Yes,
that
yes.
all the employees are paid a little more with the extra money that is being generated. I hope so.
We
But
even don't know whether extra money is being generated or not.
oh my God. But thank you so much. No offense, but I just
Sure,
wanted to
sure.
ask these questions, and you seem to be the perfect person to, have the answer. So thank you very much.
Thanks a lot. Okay, so I will go ahead with the rest of my presentation. I see that I have about 15 minutes left. So I'll give what I promised, that few tips on what we as editors look forward to in a manuscript. So when we get a manuscript, when we receive a manuscript, we ask these questions. Is the paper suitable for the journal, or is it too specialized? Is the research significant? Is it different to the prior work, and how different it is? And are the results set in the right context? And finally, do the paper adhere to the ethical guidelines? So these are the different parts we look at. First, we look at the title. So please make sure the title is descriptive, but specific and concise. I know this is contradictory, but everything about life is about balancing. So just try your best to balance the words in the title. So try to include as many as keywords as possible, and preferably avoid abbreviations, because they are not picked up by the search engines later on. This is an example of a very bad title because it doesn't say which metal catalyst, what kind of coupling reaction, etc. This is example of a good title because it is very specific, concise, and contains many keywords. Okay. Next, we look at the cover letter. So there are four main criteria in a paper. So the hypothesis, the innovation, the evidence or the data, and the clarity in the arguments. The cover letter addresses the first two questions, whether it's a clearly stated purpose and there has been a significant advancement made in the paper. And if those two criteria are satisfied, then it increases the probability of the paper going for peer review, not for publication, but going out for peer review. Here is an example of a bad cover letter, which is empty, nothing is there. This is not much better either because it doesn't say anything about the paper. This is much better. You see the words which I have highlighted with brown. So even if you read quickly, you would know what the paper contains. The structure of the abstract, try to put something important and new at the beginning, something important and new at the end. Don't make the middle part too long, otherwise the yawn will take over. Avoid too many general statements if it is a topical journal. For example, Chem Biochem, Chem Electrochem. So by the name itself, you can see that it's a very focused journal. So the general statements are redundant. The readers already are aware of them. Now, why I was emphasizing on the title and the abstract, because they are searched separately by the search engines. For example, you see here, the search results on Google are cut after 60 to 80 characters, depending on the device you use. So try to place the most important concept at or near the beginning, and try to avoid influence effect of, those doesn't add anything to the title. Very quick tips, very briefly, some things I want to talk about writing. Writing is hard because the author wants to write about a blue car, but the reader doesn't know what kind of a car it is, whether it's a toy car or it's a Tata Nano or a Volkswagen Beetle, don't know. So what to think before you start writing? Why did I do this work? How did I do it? What did I find? So you can create a quick outline, which is a written plan of the organization of the paper. The outline contains very little text. Do not think chronologically, but in the order of importance. And all the co-authors should agree before you start writing the paper. Now for some language tips, here are some resources over there in the internet. You can use it. Again, I'll pause for 5 seconds maybe. What does this sentence mean? Consequences of erudite vernacular utilized irrespective of necessity. Okay, in the interest of time, I will go ahead. So it means problems with using long words needlessly. So there was a paper, so you can see 15 years back, 16 years back. This was the title of the paper, and it says that basically there is a negative relationship between the complexity of a text and the judged intelligence of the author. So needless complexity leads to negative evaluation. So you would not want your readers to use the dictionary while reading a scientific paper.
Dr. Pal,
yes.
Sorry to interrupt. So if you could wrap up in couple of minutes or something, we can have 2-3 minutes for discussion or a couple of more questions.
Sure. So I'll skip this part. Here are some examples how you can simplify your writing. So you can try using the verb forms instead of noun. That will reduce some number of some words. You can try using shorter words. And then I was going to talk about a bit on the introduction. As you can see, the introduction can mainly be defined by the 3 I's: inspiring, informative, and interesting, and preferably not incredibly long. For the results and discussion, support any claims that you made in the introduction. Discuss the most critical data and do not ignore the anomalies because it triggers suspicion. For regular manuscript, for the middle part, try to use the principle of chunking. It helps a lot. It is easier to digest. I won't go through the experimental section or supporting information. For the graphics, I would say try to make it as clear as possible, not aesthetically beautiful. Try to increase the clarity. That is more important. Try to be consistent in the graphics, not using, you can see within brackets here and then slash here. Try to be consistent. For the table of contents, most of the journals, they use the table of contents these days. It is very important that you revise the words carefully. So how are the reviewers chosen? They are chosen as per their expertise, publication record. We do take into consideration the names authors have suggested. We do have internal reviewer suggestions, and then there is the editorial board and our experience as editor. While you are suggesting reviewers, please don't suggest your friends. Preferably avoid suggesting Nobel laureates unless you are submitting to a very high impact journal. And this is the format I think anyone would prefer: the name, affiliation, and why. If you are appealing against a decision, please write a detailed letter to the editor, include evidences, citations, keep it objective, and avoid making things personal, and keep a cool-off period before you start writing the letter. For revision, try to refine it as much as possible. If you disagree with a comment, still give your argument as to why you disagree with the comments. Try not just to do the things specifically mentioned. For example, here, if the referee says papers by X and Y groups are just 2 examples, the author thinks I need to cite papers by X and Y, but no, that's not the case. Try to do another literature source and include more papers. We do offer transfers, mostly to lower tier journals. Try to consider them because it helps relieve pressure on the peer review process and also expedites the publication process. What you can do as an author, you can make your library aware that you have published a new article. You can share your article with your friends and in the social media. And finally, what we as editors, what else we do other than handling manuscripts? We do go for acquisitions. We check out new trends, developing fields. We do attend conferences, nowadays virtual conferences, as I'm doing here. We do conduct author workshops. These are the institute visits I started in 2019. So I was able to visit a lot of institutes in 2019, but then COVID came in and we started virtual workshops. So we are open to proposals for conducting right now virtual workshops, but later on when things open up, we are open to proposals in-person workshops. Please feel free to reach out to me at ppal@wiley.com. If you're interested in holding an author workshop, or even as a part of many institutes are introducing this scientific writing course. So we can also do an author workshop as a part of that course. So thanks a lot for your attention. I'll be very happy to answer questions now or even later. You can email them to me here. Thank you. Thank you so much.
Thank you, Dr. Pal. Any questions? We have time for maybe a couple of questions. So if anyone has any question, feel free to unmute and ask directly to Dr. Pal. Yeah, so okay, I kind of have one question which actually Shobana was asking earlier. So regarding this open access, so the journals are considering, let's say, making it open access after a certain period of time. I mean, because there are some provisions, for example, some of the older things are also now behind a firewall. So is there any kind of consideration regarding towards that regard, or is, yeah?
So basically, I think I showed in one of the slides that the author can, there is an embargo period of 12 months after which the author can put a version of the published paper in their own website or the institute website. But overall, so in Europe, there is a big drive for open access, but not so much, let's say, in US or in China or in India. So it depends a lot on the funding agencies. The big drive in Europe is actually coming from the funding agencies, that you need to make your work accessible to everyone, not just people who pay for it or behind a paywall. So, but I'm not aware of any drive that they would open it or rather make it open access after some time, the entire issue of a journal or something like that. No, I'm not aware of any such thing.
Okay, so thanks a lot, Dr. Paul, for an interesting outlook for this editorial process. I think since we don't have any more questions, if you have questions, probably we can ask, reach out to Dr. Paul, or maybe we have some interaction session after this sometimes. So Sunita, I can hand it over to you. Thanks a lot.
Thank you so much.
Yeah,
for,
thank you,
inviting me.
Dr. Paul, and thank you, Dr. Bibu, for the organizing the session. So now we move on to the next session, that is the mini talks by the student. And the chair for the next session is Dr. Nandini, and we'll follow the same format that we followed for the previous session. So we'll have 2 talks and then a brief question answer session, and then followed by another 2 talks. So Dr. Nandini, you can take over from here.
Yeah, thank you, Dr. Sunita. So the first talk is by Jyoti Sharma.
Yes, hello.
Yeah, please start. Yeah.
Ma'am, is my screen visible?
Yeah, it is.
Good afternoon, everyone. Today I will talk about my work on self-propelled camphor rotors. Before I start, I thank the organizers of this conference for giving me an opportunity to present my work here. This work was done under the joint supervision of Professor Debendu and Professor Puneet, and my collaborators were Professor Veronique, Professor Satish, and Ishant Tiwari. Self-motion of camphor or its derivative is an example of solid artificial interfacial swimmers. This system has been explored in a lot of different numerical and experimental settings, one of which was earlier shown by my colleague Ishant Tiwari during this presentation. In this presentation, we will talk about the camphor ribbons, which are a rectangular sheet of paper with camphor infused on them by dipping them in camphor and ethanol. This camphor infused sheet is what I will call as a camphor rotor or camphor ribbon interchangeably during the presentation. So when we put one such rotor on the surface of water, it moves either in clockwise direction or anti-clockwise direction, and its initial direction of rotation is decided by the initial fluctuations. So why does it move on the surface of water? I will explain with this schematic diagram. So once a camphor particle touches water surface, it forms a camphor layer around it. Any initial inhomogeneity in the distribution of this layer leads to a net surface tension gradient around the particle, and hence a acceleration towards the higher surface tension, which in this case is towards my left-hand side. So then we put two such rotors on the water surface at a distance less than twice the length of a single ribbon. And in this case, we were able to see two modes of synchronization, namely co-rotating and counter-rotating. In co-rotating, both the rotors move in same direction, while in counter-rotating, they move in opposite direction. Furthermore, we have experimentally perceived that counter-rotating mode of synchrony is more robust than the co-rotating mode. After this, we searched for the collective dynamics of multiple such rotors placed in different geometries, of which sketches I have shown here. And this is the video corresponding to 5 ribbons placed on a star configuration, such that this one is moving in opposite direction and all the other 4 in the same direction. So in the case of multiple geometries, we were able to see rich variety of configuration by switching the direction of rotors. And in all of those configurations, again, we were able to see rotational synchronization when the distance between each rotor is less than LC again. So then after that, we looked for chimera-like states in this system. So chimera states are spatio-temporal pattern in an ensemble of identical oscillators, which are described as coexisting synchronized and unsynchronized groups. So this field came into limelight in 2002 with remarkable discovery of Kuramoto and Batoktok. And later on, these states were dubbed as chimera states by Ibrahim and Strogatz in 2004. The word chimera is inspired from Greek mythology character whose body consists of 3 animals' body shown here in this picture. So in our experiments, we put again 3 rotors on a triangular geometry. However, this time the distance between them was slightly greater than LC. In this setting, we were able to see a synchronized pair, which in this case is 1, 2, and 2 unsynchronized pair, which are 1, 3, and 2, 3. So this simultaneous existence of synchronized pair and 2 unsynchronized pair is what we are calling as chimera-like states in active rotors. Furthermore, the existence of chimera is proved by the phase plots shown over here, which were fetched by the image analysis of white dots on this ribbon. So with this, I will conclude my presentation that we were able to see 2 main collective features in the case of coupled self-propelled rotors, which were synchronization and chimera-like state. Furthermore, we have formulated a numerical model using Yukawa potential, which in the interest of time, I have not presented here. If anybody would like to know about the details of the model or more about the experiments, I would be happy to share later during the interaction session. With this, I thank you all for attending my presentation.
Yeah, thank you, Jyoti, for the perfect timing. And yeah, questions we will take up during the interaction session. Okay.
Yes, I will stop sharing.
Yeah, thank you. Tanushri Roy is the next presentation, and the topic is modes of synchrony in self-propelled pentanol drops. Tanushree, are you on mute?
Yes.
Yeah.
Is my screen visible?
Yeah, it's visible. Please start.
Okay. So good afternoon, everyone. And first of all, I want to thank the organizers for this soft matter conference. So here I will talk about the emergent modes of synchrony and the types of synchronization which we have observed depending on the number of self-propelled pentanol drops in the system. So before moving on, I want to thank my collaborators, Dr. Sudhanshu, Professor Manuel, Professor Veronique, and Professor Puneet. So before, 1 minute. Okay, so before sharing the results, let me talk about the main effect, which is well-known Marangoni effect. And that was first identified by physicist James Thomson in the so-called Tears of Wine in 1855. But this general effect was named after this Italian physicist Carlo Marangoni, who studied it for the first time in detail in 1865. But till then, the main theoretical framework was missing, which was given in around 1875 to 1878 by J. Willard Gibbs. So what is this tears of wine? So when you have a binary phase, that's it, that let's say the wine, which is basically the mixture of alcohol and water. So in that case, they both, the alcohol and water, shares different rate of evaporations. As well, we know that the surface tension is also hugely different. So for alcohol, it's the lower surface tension, and for water, it's a higher surface tension. So due to that, in the interface, it experience a net stress, which causes the liquid to go upwards around the wall, and it goes up along the surface of the vessel till it crosses its own weight. So after certain millimeters of rising, due to gravity, it falls back and it forms the shapes of tears, which is known as tears of wine. Now, how it is related to the movement of alcohol drops. So this is one explanation given by Nagai et al. At 2007. So if you can see, this is the pentanol drop, and these are the black dots are the pentanol molecules, which is coming out of this drop. So if there is a almost similar concentrations of pentanol molecules around the drop, then it will cause no movement of the drop. But if there is the heterogeneity is there in the concentration profile of the pentanol molecules around, then it feels a net force, which is also evident from this graph. So if we see that in the rear side of the pentanol drop, you have this gradient, and on the front side, it follows this gradient of the pentanol molecules. So you can see that there's a clear difference in the change in the gradient, which is causing the movement of the pentanol drop on the aqueous solution. So this is the main effect with which we have observed the oscillations of a single pentanol drop first. And this is our experimental setup, where this channel was introduced on this surface on this base solution, and the drop was powered onto this channel. So you can see this nice back and forth oscillations performed by a single pentanol drop. Then we were interested to observe the dynamics of two drops, where we have observed that nice antiphase oscillations, which is evident from the time series. This is corresponding to drop 1, and this is corresponding to drop 2. You can see that they share a nice out of phase oscillations. So if we plot displacement of first drop with respect to displacement of drop 2, it shows this curve along 135-degree line, which is clear evidence that they are in out of phase. Then moving on to the dynamics of 3 pentanol drops, we have observed relay synchronization. By that, what I mean is that this intermediate drops, this middle drop, that is drop 2, it is acting as a dynamical relay between these two outermost drops, which are far apart from each other. But this middle drop is acting as a relay so that it is trying to adjust the dynamics in such a way so that drop 1 and drop 3 will always be in phase, but the intermediate drops will be in out of phase with both. So which is evident from the time series for individual drops as well as from the phase space plot. Then moving on to the dynamics of 4 pentanol drops, we observe the similar dynamics where consecutive pairs are sharing out of phase oscillations and alternate pairs are sharing in phase oscillations. By that, what I mean that if you see 1 and 2 that are antiphase, also 2 and 3 are antiphase, and the same is for 3 and 4. But if you see 1 and 4, they are also in out of phase oscillations. So with this, I conclude my talk and thank you for your attention. I would like to take questions.
Yeah, thank you, Tanushree and Jyoti. Any questions for both of them? Yeah, Dr. Priya, you can go ahead and answer.
I'll begin with my question for Jyoti. Hi, Jyoti. Very nice work. It was very interesting. My question is that what would be a dampening effect in your system? Like what would cause the system to finally slow down?
Ma'am, this is mainly because of two things. As the time goes, the fuel on the strip is decreasing because it's submitting on the into the air and onto the water surface. Secondly, as the time progresses, the surface tension gradients on the water surface are diminishing. So these two collectively lead to decay in the angular frequency of the rotor with time. That's what we do.
Thank you. My next question, can I continue? It's for Tanushree.
Yeah.
Yes.
What is the perturbation that you're giving to the system for the drops to start oscillations?
So when we are starting with the system, we are not perturbing it externally. So we let the system evolve. So with time, the system itself decides the modes of synchronization. So there is, from our side, there is no external perturbation.
So the act of just placing the drop starts the oscillations then?
Yes.
Okay. Then how are the multiple drops placed? Like, are they placed simultaneously or a technical question experiment-wise?
Yeah, of course. No, in case of multiple drops, we introduce the first drop, and then after observing 2 and 3 stable oscillations from the first drop, we put the another drop. But while putting the second drop, or you can say the next drop, we try to maintain that the first drop should be at some distance when we are putting next drop, because there is a probability of collision at the first place that can lead to breaking of drops. So that we want to avoid.
Was your video a real-time oscillation, or was it sped up? Oh, it oscillates that
real
fast.
Time.
Okay,
yes.
So then, so is it quite difficult to every time maintain that distance between your drops while placing it? So let's say for your 4-drop system.
Yes.
Would your modes have be affected by how far or how quickly or how accurately you place your drops?
We tried with, if I understand your questions correctly. So yeah, it was definitely very challenging, because most of the cases, in case of 4 drops, it was leading to breaking of drops or coalescence of drops in some cases. So it was very challenging. But we can assure about the dynamics, because every time we perform the dynamics, there were 2 dynamics was always observed, and I showed the robust one, the relay synchronization in case of 4 drops. And this has been observed irrespective of the initial conditions. So it doesn't matter how we are putting the drops, as long as
they
we
always
maintain.
End up.
Yes.
So if you're successfully able to place your drops, they'll always synchronize in that particular modes itself.
Yes, robustly. And there was another dynamics that I did not show because of the time constraint.
Sure. Thank you. Thank you both of you.
Thank you.
Okay. Dr. Sunita, any question?
I had the question about the coalescence, so that was already asked and answered.
Okay.
So thank you, Tanushree, and thanks, Jyoti.
Okay.
Thank you, ma'am.
Yeah, thank you. So we move on to the next speaker. If anyone else has a question, we have 1 minute, or else we will move on to the next speaker. Okay. The next speaker is Derek. Derek Cyrus, and the topic is hydrodynamics of flagellated bacteria in dense suspensions.
So good afternoon, everyone. Are my slides visible?
Yeah, it's visible.
So good afternoon, everyone. My topic is hydrodynamics of flagellated bacteria in dense suspensions. And dense suspensions are interesting because they offer various non-trivial collective behaviors. So for example, we see here two tracer particles. They are moving in a synchronized motion. And this is due to the fact that the suspension they are in, the bacterial suspension they are in, acquires a collective synchronous circulation. On the other hand, in this bacterial suspension, we see that the tracer particles are moving in a turbulent manner. And here, there are swirling motions and jets which are seen. And from these, the patterns we have seen suggest that hydrodynamics might play an important role in the overall suspension dynamics. So the main idea is that when a bacteria or a swimmer is passing through a fluid, it disturbs the fluid, and that causes it to interact hydrodynamically with other swimmers, and hydrodynamic interactions being long range may have the ability to cause the interesting features like the videos we saw in the previous slides. So the one way to look at it is to see the velocity field of a swimmer. So on the left here, we have bacteria, and here is the experimental flow field or the velocity field around it. And we see a qualitatively similar velocity field in a minimalistic model of a bacteria. And we find that it's qualitatively similar. So it shows that minimalistic models do have a value in trying to attain the suspension hydrodynamics. So now we go on to discuss our model of this bacteria. And in dense suspensions, collision events are more likely to occur. And in such an event, it is likely that the flagella can tilt. So our model incorporates this fact that it allows this tilting of the flagella to occur. And this leads to this model having a non-axisymmetric part. So here in this schematic, we have the model decomposed into an axisymmetric part, a non-axisymmetric part, and an active torque part. So the axisymmetric part, as the flow field due to it has been analyzed and calculated by Adhyapak et al. Previously, and we have gone on to calculate the flow field and the contributions from the non-axisymmetric and the active torque part. The main challenge being to ensure that at the surface of the swimmer, the boundary conditions are satisfied. So in order to get the velocity field of our swimmer, we solve the Stokes equation in the presence of our model. And in order to get the hydrodynamic interactions and to calculate the velocities with which these swimmers will move, we apply Faxon's theorem, and we get the velocities in terms of the propulsion velocities and the background flows. In this slide, we plot the velocity field of a bacteria as a function of bending angle. And we see that at large bending angles, large scale swirlings do occur in the system. And now we also analyzed the propulsion, the self-propulsion and the self-rotation of this model. And the main interesting feature in the self-propulsion is that even though the force on this, the swimmer applies a force on a particular direction, it can acquire a velocity in a direction perpendicular to this forcing direction, as is seen from the non-zero value of this green curve. For self-rotation, we find that for non-zero bending angle, we get a non-zero active rotation of the swimmer. And finally, we show a preliminary result of a simulation of two swimmers undergoing a collision event. And we have done this to incorporate this. We have added steric interactions, and to do so, we have incorporated a physical flagella by utilizing slender body theory for our model. So using this, we have calculated the propulsions for our system However, there are a few more interactions which we have to incorporate for accuracy. And so this is currently a work in progress. So these are my references, and thank you.
Yeah, thank you, Derek. Next speaker is Ambarish Srivastav.
Yes, ma'am. Can all of you hear me?
Yeah, please share your slide.
Okay, is my screen visible?
Yes.
Okay. So my slides are also visible.
Yeah, please do.
Yeah. Okay. So this is I am Ambarish. I am working with Tapanchanda Adhyapak at IISc Tirupati, and my topic is hydrodynamics of flagellated microswimmers in confined fluids. So microswimmers have become an active topic of research in soft matter physics, and understanding their individual dynamics and collective behavior involve challenging physics and confinement. Actually, that is because confinement modifies the hydrodynamic flows because of uh, they add some additional boundary conditions to be satisfied, which result in some surprising and rich phenomena. And although many experiments and simulation have demonstrated some of these interesting phenomena, but still a lot remains to be explored, and there are many open questions in this field for microswimmers in confinement. So I show some two experiments. One is done by Turner and Berg. So this is a movie of E. coli bacteria. So this is they are moving in bulk, and here they are moving in confinement or near a boundary or substrate. So as you can see, the motion is considerably slowed down near a boundary as compared to in bulk. Another example is interesting experiment is observed by Palaki. It is the self-organization of subcolloidal particles in confined suspensions. So these colloidal particles are actually photoactive, and when we shine light on it, they actually self-propel, and they show this interesting picture that they actually accumulate. So this is the initial configuration, all where isotropically distributed. But as soon as light is shine on them, then they actually cluster together, and this is also an interesting phenomena. So how we have modeled is, like we have modeled our swimmer as a rigid spherical cell body, and it has a flagella, and this flagella applies force on the fluid, and the fluid pushes the cell body forward, and this is the boundary. So to solve for the dynamics, we need to calculate the hydrodynamic flows. So this so how we have modeled is the flagella applies a force on the fluid at a particular point, at a single point, and this creates a flow around it. And this pushes the swimmer forward, and the translation of the swimmer creates flow around it. So these black curves are actually the direct flows, and these red dotted lines you can see are the reflected flows. So this is the flow reflected of this cell body surface, and this is the flow reflected of the cell wall. So what we do is we solve the Stokes equation to calculate the hydrodynamic flow with two boundary conditions. One is that the flow should vanish at the swimmer surface, and the flow should vanish at the wall. So we need to satisfy two boundary conditions simultaneously, and to do that, we need to calculate all these reflected flow fields via calculating hydrodynamic image fields, which is rather complex because we need to simultaneously satisfy these two boundary conditions. And the solution we get is the flow around the swimmer. So this is how it looks. You can see this is the swimmer, and the boundary is at the x-axis here, and this is the distance from the boundary. And as the swimmer approaches the boundary, so you can see how the flow field gets modified near the boundary. So this is for varying height. And suppose we fix the height and the swimmer orients itself or rotates with respect to this boundary. So this is how the hydrodynamic flows gets modified due to the boundary. Next result is the self-propulsion velocity. So if the initial flow is known, and when we place a particle in that flow, then the velocity of that particle is given by Faxon's theorem, as talked by Derek. So this is the self-propulsion velocity formula. Here V prime is the initial flow, which is present before the particle is introduced. So we need to know the flow field first. So as I showed, we have already calculated it. And from the flow field, we calculated the self-propulsion velocity of our model swimmer. And a corresponding formula also exists for the angular velocity as well. So to calculate V prime, what we do is we calculate the net disturbance flow experienced by the swimmer, which is the flow due to the point force, and the net wall reflected flows. And this is our result. So these green dots and this blue curve is for the passive sphere, meaning the point force is not present. And this is the result of by Swan and Brady, who calculated it without the presence of point force for a passive sphere. And this is for our model. So as you can see, as the swimmer approaches the wall, the velocity gets reduced. And it's also less than that of the passive sphere. So
Yeah,
in
pretty
calculating
sure
this,
5 minutes are over.
yeah, ma'am, just 30 seconds. Yeah. So to calculate the angular, we calculated the angular velocity, and we found that it is always positive, and it never gets negative. But some other work we refer to. So here, this is work by Spagnini and Lavga, who calculated using far field approximation, and there they got that the angular velocity actually gets negative. So definitely we missed something, and then we found out that we missed the resistance offered by the fluid flow, because we considered the flagella applies a force at a singular point. So what we did is we introduced a physical flagella, modeling it as a physical rod, such that the force is now not at a singular point, but is actually distributed. And this distribution is given by the slender body theory. And when we incorporate this force distribution, then we actually are able to reproduce the result. And this is a ongoing work. We are working on other things. And these are my references. Thank you. Yeah.
Yeah, thank you, Ambarish and Derek. Any questions on these two presentations? Yeah, Dr. Priya. And
my question for Derek is, what was the main finding from your work? I seem to have missed that part.
Okay, so there are a couple of results. One was that when we look at the self-propulsion velocity of swimmer, so the self-propulsion velocity can acquire a component which is perpendicular to the direction in which the force is acting. So that is one of the results. The other is that once we incorporate the fact that the flagella can tilt with respect to its original orientation, then it also acquires an active rotation, which we have also calculated. And then we have also calculated for the first time the exact flow field for for a swimmer with a arbitrary tilting angle. So
is this seen in this tilting of the flagella? Is it seen in examples like nature or in bacteria?
Yeah, like for example, one is that in our group, there's also been a simulation with a more for a more detailed model of E. coli bacteria, and there have been simulations where this tilting has been observed. As well as there are some experimental observations which hint at the fact that upon collision, flagella do tilt. So that's why we also try.
So it's an out of plane movement, or just a bending within the plane?
So
The
we
tilting of the flagella.
because of our initial conditions, so the bending was in the plane. But yeah, so and of course the images which is there in the so it's not been it's not like something which is study that the tilting, whether it happens in the plane or out of the plane. So when you see the image, it will it's difficult to tell as of now. So we are trying to study this to see if this to see how much effect this has, because there will be
Sure.
collisions in a dense suspension. So the
Of
model
course.
should have the bacteria should have a way of maneuvering itself out of it. So in that way also we are looking at.
Okay, thanks. My next question is for Ambarish. What is the location of the point force? Like, how do you decide it in your model?
Okay, we fix some flagella length.
Okay.
So the distance from the center of the cell body to that point is the flagella length. So
okay. So
it
this
can be
flagella length you
arbitrarily
decide, do you decide it based on experimental findings or some average flagellar length, is it? What are the typical figures you use?
So typically we use 5 times the radius, but it is not necessary. So our model can predict the dynamics of any length bacteria. Yeah.
But does it affect based on the length that you choose of the flagella?
Yeah, definitely. So as I showed some graphs, what length. Yeah.
Okay, thank you.
Yes, Dr. Danny.
Yeah, thanks. I have a question for Derek. So when does the angle of the flagella change, or how does it change?
Yeah, upon collision with another swimmer.
Okay, but in some of the examples that you initially showed for motivation, the density was quite packed, So how do you even visualize these slender bodies to exist?
Yes.
Is that even possible at that in that density, or your model has to change?
In fact, one of the reasons, since in a very dense, as it is, a flagella very difficult to visualize, to see, and in a dense packed suspension to see the dynamics of the flagella, it's not very easy to see it happening visually. So that is also one of the a part of the motivation, is that if our modeling is correct based on our other understanding of the bacteria, so we know that the bacteria has a universal joint and it's a flexible joint. So there are certain understanding which is already there, and based on that we have modeled it. So now it will be important to theoretically also try to calculate the effect of these bending, because first of all it's difficult to visualize it also. So if the theoretical model can in a way qualitatively or quantitatively show some results like the ones which are seen, then it will also be a validation in that sense, as well as to make predictions. But currently
Right.
it's very difficult to visualize the flagella in such a dense way. But uh, when there are few bacteria colliding, then there are events which look like a tilting of flagella, which we have used as a inspiration for the work.
Right. Quick follow-up. So let's say when it does not tilt actively and there's a single microorganism, or in your model, will it keep going straight, or will it show any other dynamics? Will it turn or anything?
When it
Your model for an individual particle, it will keep going in a straight line, is it? If when it does not encounter any obstacles.
Yeah, then it will keep going in a straight line.
But you do know that individual bacteria turn after some time. So do you think you can model that by bringing in some kind of a stochastic element into your
Yes, then that will have
turning?
to be added for that modeling. So we'll add that the stochastic noise, the thermal noise, as well as the active noise can be just added as a
Right. Okay. Yeah. Thanks, Derek. A quick question for Ambarish. In one of the slides, I think you showed between a normal sphere versus your swimmer, and there didn't seem to be any qualitative difference. I know you showed quantitative difference, if I understand it right. So what does your model tell extra? Did I get that right, Ambarish?
Ambarish, you're there?
I think he's not heard my question.
Has some
Yeah.
connectivity issue. Any
Sure.
questions for Derek? Oh, Ambarish is back here.
Yes, ma'am. Yeah.
Ambarish, you heard the question by Dr. Danny? Or we can...
No.
Okay.
No.
Oh, okay. So I asked Ambarish, so in one of the results that you showed, there seemed to be no difference between qualitative difference between a spherical particle and your swimmer. There was a quantitative change when it was going towards the boundary. So I was wondering, why is that? Because your swimmer model is doing something different, right? Yet there is no. Do you have any thoughts on it?
Yes, so you're talking about the some other model with a different means not spherical particles.
Okay, I thought you compared your swimmer with a non-swimming model.
Okay, right.
But there seemed to be no qualitative difference. Is that something obvious for you, or I mean, can you comment on that?
Okay, so means without the active part and the point force, that there's only a quantitative difference and no qualitative difference. Yeah, so yeah, that's correct actually. So the point force actually what it does is just adds to the hydrodynamic flow, and it reduces its velocities and all. Yeah, because of the additional reflection flow from the point force. So it gets quantitatively reduced, but qualitative picture actually is similar.
Okay, thanks, Andrew.
May I jump on that? Just a quick comment. I mean, can I do that? This question.
Yes,
Hi,
please.
I'm Topper. Just a quick answer to that question. So yes, I mean, so quantitatively or qualitatively, the velocities, self-propulsion velocities remain very similar qualitatively. The main difference between a passive sphere and a swimmer comes in the flow field. Okay, that will actually be reflected in the hydrodynamic interactions, not in the self-propelling. So isolated swimmer, they just travel slow. That's it. But another thing is that the moment we have a flagella, we can actually study the self-propulsion dynamics as a function of the length of the flagella and so on. That has more added up richness.
Okay, thank you. Nitin, your question?
Yeah, so my question is for Ambarish. You showed that video in the beginning where when the bacteria, they were confined. So my question is whether there is any change in the tumbling rate, like when these organisms are under confinement, and whether your model can shine light on it.
Okay, on the tumbling of bacteria.
Yeah.
Yes, we can do that, but actually right now we haven't done anything on the analytical work on that. Like,
okay.
So there,
okay.
Yeah.
Yeah. Okay. Thank you.
If no more questions, then we can end this session. Dr. Sunita.
Yes. Yeah. Thank you, Dr. Nandini, and all the speakers of the session. So we have a quick break for around 15 minutes for tea, and then we'll resume our invited speaker session at 3:30 p.m. And I forgot to mention that the breakout rooms are available. So if the participants are interested to chat one-to-one, then they can use one of the rooms and initiate the conversation. Thank you.
Nice, Sunita Di.
Hi, Tapan.
Hi, how are you? Good to see you after so many years.
Yeah. How have you been? How is the new lab and everything?
So you're asking about me, my lab?
Yes. Yes.
Okay. Yeah, I mean, yeah, here.
Hi, Tapan.
Hi. Hi.
How are you?
I'm fine. How are you? Okay.
Good. We met in Regensburg. You remember?
Yeah. So, yeah, good old days.
Yeah, finally, like, I think the 4 videos which are on are all from ISC. So I see Nitin's video is on.
Yeah.
Yeah.
Yeah, we can hang out after the session in the breakout room and chat.
It would have been nice if this was offline.
Yeah, exactly. Physical, yes.
We would have enjoyed this meeting much more.
Right. That's what we miss now.
Yes.
Yeah, here actually we started going to our offices, faculties, and research students are mostly back. But BSMS students, I mean, they're slowly bringing in. I mean, not all of them are here.
Okay.
Other than that, I mean, things are getting normal. At least if you go out, then you feel normal.
I think that's the general scenario everywhere. Outside the campus life, it seems to be pretty normal. But when we come inside the campus, then there's a lot of restrictions.
Right.
Yeah.
And how are you? I mean, so you're in Mumbai now, in the campus, or?
Yeah, I haven't gone anywhere since I'll say 1.5 years. The pandemic started. Yes, so we are in the campus. So that way we have been able to visit the offices and labs, not with much of a restriction, except during the first lockdown.
I see.
So we have, but students came back much later, around February or March.
Yeah.
So most of the research students now are back in the campus, but still the undergrads, first year, second year are being called in phases. Still online teaching is going on. So.
Right. I mean, most of the cases are usually fine. I mean, so like I had it. Hi, Nitin. So I had it.
Hi, Tapan.
Yeah. Like you have said, Nitin, I mean, so most of the cases are fine. But in our institute, there have been a couple of tragedies. I mean, there was a death, the postdoc, and some parents died, parents of some faculties. And because our institute is a small one, I mean, we had a small number of cases mixed.
So shall we get started?
Yes, we can. So shall I share my screen?
Yes, go ahead. I'll introduce Nitin. He's the first speaker for today, but I'm also co-chairing with Nitin, so he will take over after his talk.
Okay, so I have already shared my screen.
Okay. Right. Yeah, it's visible. So let me just introduce you, then you can go ahead, Nitin. So our first speaker for today, welcome back to the session. Our first speaker for the session is Nitin Kumar. He's a faculty at the Department of Physics in IIT Bombay. He has a BSc in physics from Punjab University, Chandigarh, MS and PhD from ISC, and then postdoc from University of Chicago. So he works to understand the physical and mechanical properties of soft and active matter systems using statistical physics. So over to you, Nitin.
Okay. Thank you, Danny. So yeah, thanks to the organizers for inviting me for this wonderful opportunity to meet with colleagues all over the country. So I recently joined Department of Physics at IIT Bombay, and I'm in process of setting up what I call active and soft matter group. And I'm specifically interested in like 3 subcategories of this field. One is basically to build some model experimental systems to study collective behavior that we see in active matter all the time in natural world. The other part is basically to get motivated from the processes that are happening in biological world, and to create some artificial and like lab grown materials, which I call bioactive. And the building blocks, they come from, like I told you, like from biological systems. And the third part is basically to look at non-equilibrium fluctuations in these active system, and to learn about the dynamical phases and phase transitions that go in these systems. So today, mostly I'll be covering whatever I did in my postdoc, which basically falls into the second subcategory, which I have written here. And towards the end, so I'll just give you a brief introduction to what is going on in my lab. Although my lab is not ready, but my students are already working. So I'll talk about some smart robots, some programmable robots, which we are working on. And I'll just give you a few slide introduction to what those are. So basically, I'll just start by defining the term active matter, although it's not required to this audience. So let's first define what is not an active matter, right? What's a passive particle? So any system which is at equilibrium and whose energy is conserved. So those systems, they have time reversible dynamics, and one of those examples is basically pollen grains, which are suspended in water. And what they can at best just undergo Brownian motion if you look under the microscope, right? So as you can see in this movie. But on the other hand, an active particle, so it has a special property in which it can convert some form of energy into work and dissipate rest of it. And as a result, this system is completely performing out of equilibrium. And as a result, these systems typically they are self-driven, so they can self-propel, right? And one of the examples of it, like the closest to pollen grains, is basically E. coli bacteria, which we have already seen in previous talks. And you can see that the dynamics here is very different from what we can ever imagine in equilibrium physics, right? So basically, the whole aim of active matter physicists is to basically look at the collection of such active particles which have ability to convert one form of energy into another, right? So that is basically what my research interest is basically focused on. And there are two like main focus areas in active matter. So one is to just look at the collective behavior of these self-propelled entities. And I've just given like these three among many examples. So here you can see that these sheep, they all move collectively. Similarly, these ants, they can move collectively and form these weird collective dynamical state. Similarly, these bacteria here at a microscopic length scale, they can also show some collective behavior, right? And what is common in all these movies is that the energy input is at the individual particle level, and all these flows, they are so all these flows. So we are not really applying any external electric or magnetic field. So they are self-driven essentially, and there is a spontaneous orientation order, right? So this is one part of active matter which is studied a lot. But there is another relatively less looked at feature of active matter, is that the very injection of activity in materials that can also change the properties, right? So I'll just give you an example. So there was this paper in 2010. So where what they did was they just added some swimming bacteria in water, and they calculated the viscosity of the resulting solution. And they found out that when the bacteria was swimming, when it was alive, it enhanced the viscosity of the fluid, right? As compared to when bacteria was not swimming. And there is like this beautiful explanation that was given by Professor Shriram Ramaswamy's group even before the experiments were performed. And it all boils down to what kind of flows are generated by the swimming bacteria, right? So similarly, so for example, in this case, when the flow is of the form of a puller, in that case, the viscosity goes up. But if the flow is pusher, like the fluid is expelled away from the body of the swimmer, in that case, very recently, like 5 years ago, this group showed that you can reduce the viscosity down to 0. So basically, they called it basically bacterial superfluids, right? So the point that I'm getting to is basically just by injecting activity in the form of these dumb swimming organisms, you can just change the property of your material, right? So that basically motivated us to basically look at some experimental systems where we can do it in a much better way, right? So whether we can study a material with and without activity, and also look at its properties in passive as well as active state, right? So that is that brings me to the outline of the talk, which I'll be giving now. So in the part one, so I'll tell you, like, the system that I've worked on is basically biopolymer based pneumatic liquid crystals. And in the first part, I'll show you how we can just tune the elasticity of this material. So in this part, there is no activity. But in part two, we will inject the activity into the system, and we'll see how these properties, they basically change when we add activity into the system. And like I said in the third part, like just few slides, I'll tell you about the recent ongoing work that we are doing. So we are basically building some smart programmable robots, and our aim is to basically control its dynamics and the way it interacts with its neighbors. Okay, so just a brief background of what pneumatic liquid crystals are, because it's important to understand the results that I'll show. So liquid, or more generally a fluid, is basically a phase of matter where both translational and rotational symmetry is preserved, right? So here you can see that this material is disordered both in the form of its position as well as orientation. But when we increase the density of these rods, we can see that these rods, they want to effectively pack with each other, right? So as a result, they acquire some pneumatic order, which we can clearly assign by define by assigning a vector n to the local director. And here you can see that the rotational symmetry is broken. And due to this broken symmetry and this acquired order, there are also restoring forces which naturally come in this phase, right? So if you ever try to change the pneumatic order, the system doesn't like it. So it requires some finite elasticity, which can be of the two forms. So either you can splay your pneumatic director or you can bend your pneumatic director. Moreover, we can also see there are points in the pneumatic field where the order is not defined, right? So at this point, you can't really say that in which direction the rod is pointing. And these 2 points, they are basically structural defects, and they are also known as topological point defects in pneumatic liquid crystals. And a plus half defect typically looks like so it looks like a U shape, right? So it's called plus half because if we basically perform a rotation around the core of this defect, the arrow, which is like the direction in which the local order is pointing, it undergoes half a rotation, and the sense of rotation is same as in which the arrow was pointing. So therefore, a plus half. Similarly, we can define a minus half defect in these materials. So therefore, like these materials are basically liquids because they do not have any translational order, but they still have some finite elasticity. And also, these materials are very easy to visualize, right? Because the features like this orientational order and topological defects, they are very easy to track, experimentally speaking. And also, I'll show you that there is a direct relationship between just the shape of these defects and the elasticity, which is the material property that I'm talking about, which comes in very handy when we want to understand the changes of properties of materials with respect to activity. And before I show my results, I must highlight that this field has grown into its own subfield, which is known as active pneumatics. And I've just given two instances of that. The first one was by, again, Ramaswamy's group, where they basically shook these copper rods on a vibrating plate. And you can see that there is a motion of this plus half defect in this direction, and there is a pneumatic order. Similarly, there are other experiments with microtubule and kinesin extract. You can see complicated dynamics happening here, right? But the drawback of these experiments is like you can't really create a passive state out of this, right? And also, it's not clear what is the activity parameter, right? What is the experimental knob that you can turn just to change in order to change the properties of these complicated flows. And therefore, we basically switched to another system. We basically invented another system, which is now an actin-based pneumatic liquid crystal, and that's what I'll talk about in the rest of the talk. So actin is basically a biopolymer. Okay, so it is about 8 nanometer in diameter, and its persistence length is about 10 micron. And in order to turn this system active, we'll use something known as myosin motor. And these biopolymers, they form basically the major part of human muscle, like animal muscle. So the way we do this experiment is we first polymerize this actin, monomeric actin, but in special ingredient that we use is something known as capping protein, which we can use to control the length of these filaments. So as a function of this capping protein in the solution, we can vary the length of our rods, right, of our actin filaments. And the way we perform the experiment is we create an oil-water interface, which is stabilized using a surfactant layer, and we add these actin filaments from top, and then using depletion interaction, we crowd all of them was a two-dimensional monolayer. And eventually, they all form a beautiful looking pneumatic liquid crystal, which we can visualize, and all the proteins are fluorescently labeled. So I'll just show you the formation of a typical pneumatic state of these actin filaments. So I'll just skip these details like the imaging and all, but let me play this again. So initially you can see that when the concentration of these filaments, so you can see like these dim looking rods, so they are actin filaments. So when concentration is low, so you have an isotropic phase, but as the concentration increases, system eventually moves into a pneumatic state. And we can also, towards the end, identify these topological defects. Okay, so towards the end, where these circles represent wherever we have these topological defects. So there are plus half and minus half defects. The first result, which is like non-active result, is that what we showed was that we can change the shape of these topological point defects. Like here I have highlighted the plus half defect as a function of the filament length. And we can see that there is a dramatic change in the shape of a plus half defect. And we later figured out, so when we quantified the shape of this defect by just plotting the angle the director makes with the tangent, a circle drawn around the core of the defect as a function of its angular component as shown here, we can see that the graph changes its form. So it goes from convex upwards to concave upwards. And we figured out that this is essentially just because the system has different values of elasticity. For example, for a V-shaped defect, this system doesn't want to bend that easily. So therefore, the bending modulus, which is K3, is much greater than its play modulus. But it is totally opposite when you have a shorter filament liquid crystal. So essentially, we have a system where we can tune the elasticity of this material just by changing the length of the filament. And I'll not go into details, but there is another way we can also dope our liquid crystal with something known as microtubule. So it's also another biopolymer, but it is much more rigid. So it adds additional rigidity to this system. And I'll not go into details. So there is a complete control over the elastic property of this material that we have created. Okay, so this is like the end of the part one, but in part two, what we'll do is we'll now inject activity into this system. So far, there is no activity. And the way we do it is by putting myosin motor into the system. And what these motors do is they basically walk on these actin filaments. And the energy source is basically ATP to ADP hydrolysis reaction. And if you want to get an idea like what's going on, so this is a beautiful animation where it's shown that how a kinesin motor moves on a microtubule. And this myosin motor also does a similar dynamics. The only difference is that in this case, there are many legs attached to this motor. But it is when it moves on this actin filament, it creates flows and forces. So what we do is we add these motors from top, they quickly polymerize and they attach to two actin filaments. And when this motor wants to walk on these filaments, so if these filaments are pointed in opposite directions, so they will slide away. And this very sliding motion creates these hydrodynamic flows at microscopic length scale, which is about the length of the filament. And I'll just show you the movie, the experimental movie. So time now is at -42, which means that I have not added motors yet, and motors is basically activity. And when time goes to 0 and when I play the movie, you will see how the activity changes the dynamics. So when I add these motors, which are not visible here in this movie, you can see that very complex and complicated flows they're setting. And this is what we are trying to understand and control, essentially. So there are various features that we see. So the first one is that when we add motors, so motors are shown on the right side, by the way, and actin is on the left side. So when we add motors, we can see that a uniform pneumatic spontaneously breaks into two topological defects, +1 and a minus, +half and a -half defect. Not only that, these defects, they also start propagating. So for example, in this movie, you can see that a +half defect has a ballistic motion. So it moves towards its head. On the other hand, a -half defect, it's statistically stationary. So it doesn't have any directionality in its motion. And this is understood very well by a theory which was proposed years ago, that whenever we have these elongated extensile stresslets, and if you create a pneumatic out of it, that pneumatic is unstable to the hydrodynamic flows. And eventually this pneumatic state of these stresslets, it breaks down into two topological defects. And this +half topological defects carries some polarity. So it moves in certain direction. And in the next, yeah.
4 more minutes.
Yeah, so I'll take 7 minutes. That's all. Okay, so in the next part, we look at the dynamical properties of our experiment. So what we did is we basically measured the pneumatic correlation function, which basically tells you what is the probability of two actin filaments to point in the same direction. And when we did that, we saw that when we add activity into the system, the correlation length was much shorter in the presence of the activity. Moreover, we also analyzed the velocity correlation function, and that also showed similar decay as a function of activity. And not only that, we basically did this experiment over a vast range of myosin concentration. We basically saw this scaling, that these correlation lengths were scaling linearly with the inverse square root of the concentration of myosin. And by the way, this concentration is something which we are looking in the microscope. So remember, these myosin motors we can directly visualize. And we also worked with our collaborators. We came up with this hydrodynamic model. And here we saw that, so in that Navier-Stokes equation, they add this activity by hand. And the strength of that activity is alpha, which tells you that how strongly these filaments are sliding away with respect to each other. And the result and the outcome that we saw was basically the myosin puncta density that we see in experiments is nothing but it's equivalent to the microscopic activity that they are putting in the model, right? So basically, the conclusion is that the myosin density or myosin concentration in our experiments is a direct marker or measure of the activity in the system, which can be easily controlled experimentally. And there are also some interesting features like these topological defects, which usually when in equilibrium or when there is no activity, they will always attract each other in order to minimize the free energy, as shown by this graph. So if you plot the separation, but when we add activity into the system, these defects, they can repel each other. And not only that, since it is a competition of activity and elasticity, just by varying the concentration of motors in the system, we can even stall these defects. So we can control the dynamics of these defects. So we can either make them attract, repel, or stay put, right? So these are some easy things that we can do with these systems. And finally, we also can basically measure the elasticity of our system. So you can see in this movie that when we add in the motors, when we inject activity, the shape of this defect goes from something which looks like V, something which looks like U. And we already know what does that mean. It basically tells us the ratio of splay to bend elasticity in our material. And when we plot that ratio as a function of activity in the system, so we can quantify that very precisely. And the conclusion here is that in the presence of activity, the system has completely different properties, different elastic properties. And this is similar to what those people did with bacteria solution, like how they could change the viscosity. We can change the elasticity of a pneumatic liquid crystal. And that ends the part 2 of my talk. And just another 2 minutes, I'll show you something which is going on now, ongoing in my lab. So basically, the motivation is that the active particles that we know, in nature, they can do all kind of stuff, right? They can move, they can spin, rotate, they can follow their neighbors, they can sense obstacles, track gradient fields, react to external stimuli. And all these features or all these properties, either individually or together, they give rise to various rich phases of collective dynamics, right? That's why what I discussed with my PhD student, and we came up with a solution that whether we can put all these properties into a single experimental system. And he built this robot, which is actually a programmable robot with a processor inside, which you can basically program according to whatever dynamics we want to extract. And this is just typical top and bottom view, and it comes with sensors, infrared sensors, with which it can identify or it can sense the obstacles or its neighbors. And depending upon the program that we have loaded, it can undergo different kinds of dynamics. And this is how the rudimentary first version of this robot looks like, but we are working on it. I'll just show you like 3 typical dynamics it can undergo. So it can go forward, it can go backward, it can spin, and all these programs are preloaded. Just to typically, like if you put inside a box, it can also undergo run and tumble dynamics and so on. Like, so this is just a teaser essentially, but when we put many of them together, so we are hoping that we should see some rich dynamics, that rich phases that we see all around the nature, right? So that is the hope. Yeah, so with this I'll end my talk. So these are the collaborators in my postdoc days, and thanks to the funding agencies. Thank you so much.
Thank you, Nitin, for the very nice talk. The floor is open for questions. Yes, Bibu Ranjan, go ahead. We can't hear you, Bibu. I think you're muted.
Okay, so I think there was a problem with my mic. Yeah. So hi, Nitin. Nice talk. Nice.
Thank you.
So my simple question there is that in the actin, what was the typical length distribution for your actin filaments? Because beyond certain length scales, you will hit the persistent length. So I mean,
right.
or do you have any kind of comment on that? If you just keep on elongating it, I mean, beyond certain, do you still see those kind of activities? And
yes.
Again, we continue the second question so that you can answer both of them. So you don't see any branching there. For example, you don't have a R2-3 protein, and if you put such kind of branching, then you will completely easily and you will form networks. I mean, rather than having some active fluids. I mean,
okay. Yeah. To answer your first question, so this is usually done in a buffer solution. So when we have no capping protein, usually the length of these actin filaments is about 10 to 15 micron, and over that length scale, they are basically very, very floppy. And one of the requirement for forming a nematic state is that you should have a well-defined nematic director at individual molecular level. So if your individual molecule or whatever particle is bending, you can't really define that nematic director. So therefore, we have to go to a very short length scale, like 1 or 2 micron, and we can tune it. So it's right that there is a distribution, but it is a well-defined peak, which is around 1, and it is very tunable just in as a function of protein concentration. To answer your second question, yes, like there are various actin binding proteins like ARP2-3 which can form this branching. So that is a very good question. So I have not really looked at it. And I don't even know many in vitro experiments which look at, active experiments which look at the kinds of structures that will form when you inject activity into the system. But ARP2-3 is one protein which I couldn't get my hands on to. So otherwise, I would have done something for sure. Yeah.
Okay. Yeah. Thanks a lot.
Dr. Tapan?
Yeah. Hi. So Nitin, I mean, I have just 2 questions. First of all, this actin nematics that you prepared, is it like a dry system or there is some kind of fluid?
No. It's a wet system. So it is suspended in a fluid.
I see. Okay. That's why you see so much of the fluctuations in the.
Yes. So there are hydrodynamic flows.
Okay. And the second question is that, I mean, so do you see any SMYIM order in it?
That is a good question, but my knowledge tells me that for SMYIM order, your aspect ratio has to be very small.
Right.
Actin is like 8 nanometer wide, and even if you go to like 10 nanometer or 1 micron, the aspect ratio is again falls into the nematic phase. But we can create smectics in vibrated granular matter. And I know like there is hardly anything which has happened in this field experimentally, like active smectics and so on.
Right. So I remember actually that there has been indeed an experiment long time back in these kind of systems, actin filaments. But like you said, I mean, so they see density fluctuations, but those are like really, I mean, the undulations are really huge. I was wondering if you increase the density or something, you might get stable stripes.
No, I never saw smectic in my system, actually. But I believe if we go to shorter and shorter length, then we will eventually see smectic order. But at that short length, it's very difficult to crowd these actin filaments, and it's very difficult to see them anyway. So there are these technical challenges.
Right.
If we work with these kind of system, but in other systems, we can create smectic order, like vibrated granular rods and so on.
Yeah. Okay, thanks.
Tanushree, you can go next.
Okay, hello, Professor Nitish. I am Tanushree.
Yes.
Okay, so I have 2 questions. The first one may be silly questions. Like when we are talking about the filaments, so I just want to know, like when the polymers or the, let's say, filaments are cross-linked, like crossing over each other, is that considered as a defect also?
No. So these filaments, they never cross each other. So they are all lying parallel to each other. Okay, so let me show you. I don't know. So here, maybe you can see, it's not very clear, but you can see that all these filaments, they never do this, because that is not really a nematic. So they are all crowded onto 2-dimensional surface, and they are all forming a 2-dimensional, like 2D thin layer. So they are all lying parallel to each other. But defects are a much bigger phenomenon. So defects happen over a much larger length scale as compared to the filament length.
Okay, but like as we understand, maybe in the cell, the filaments do the cross-linking also.
Yes.
So in that case, how can we correlate the defects with that part when it is happening inside the cell?
No, so these things never happen inside the cell. So in fact, these are not really physiologically important questions as far as I know, because inside the cell, actin is doing treadmilling. It is undergoing depolymerization and polymerization. There are hundreds of cross-linkers which are serving different purpose at different time. So as far as I know, there is no active nematic inside the cell, and there are no such defects. This is totally an artificial system which is created out of the cell.
Okay. Yeah. And my second question is, in the last slide, you were showing some teaser about the robot. So in case of collective, to study the collective dynamics, when you are introducing, let's say, multiple robots, what will be the mode of interactions between them? I mean, how they will couple to each other?
So all that we can tune. So that is the hope. So when these robots sense each other, we can either make them move in the same direction or cause them to spin and so on. So we can do all kinds of things. So we have to preload a program inside them, and we can make them behave in whichever way we want. But right now we only have one of these, and it's still undergoing some changes all the time. But our hope is to multiply them, maybe get 50 or 100 of them, and then we'll see what is the most interesting thing to do with these particles, essentially.
Okay. Thank you, Professor, and a very wonderful talk.
Thank you so much.
So in the interest of time, I think if you don't mind, we can have questions towards the interaction session.
Sure. Yeah, I'll get in touch.
Thanks, Nitin, for the nice talk. Now up to you to clear the session.
Thank you so much. So I think the next speaker is Professor Tripta Bhatia, right? So
no, I'm not yet professor. I just
okay. So Dr. Tripta Bhatia. So she did her PhD from RRI Bangalore in 2012, and she did a couple of postdocs after that. So first one was in University of Southern Denmark, and then the other one is in Max Planck Institute of Colloids and Interfaces. And right now she is in IISER Mohali in Department of Physics. And her research interests are soft matter and biophysics, broadly speaking. And yeah, so the floor is yours.
Thank you.
You can share your screen.
I will have to go forth and back because some of the movies I will have to play separately.
Okay. Okay, that's fine.
So is it visible?
Yes. It's not full screen, but it's visible. Yeah, now it's full screen.
Okay. So hello everyone. I'm Tripta. I joined e-SMYIM this year in February. I hope all of you can hear me. So I'll just continue. So I'm interested in micromechanics of biomembranes. And first of all, people's first. So this is my team. So far I have a postdoc and I have a funding from Indian Institute of Science, Education and Research, Mohali. They gave me a startup and then I also got Ramalinga Swamy re-entry grant to work with an ion pump, sodium potassium ATPase in collaboration with Professor Cornelius, who will provide us the pump. We are also socially active on media. So the outline of my presentation is I will first tell you a little bit about biomembranes and why I find them very exciting. Then I will discuss remodeling of the biomembrane and why it can be active as well as non-active or passive. Then I will a little bit tell you about what do I actually mean by micromechanics. And then I will talk a little bit about the pump. Then the aim is to actually build up synthetic cell in the lab. So I will a little bit give you a flavor of that. And then I will also tell you about the lab status at the moment. So these are some key publications. So only the first one is what came just now, accepted in Advanced Science, which have my affiliation at ISCR. But the others are all during my postdoc. So currently I will try to stick to what I plan to do here at ISR. And then I will stick to the funding for which I got to work with the pump. So in general, when we talk about biomembranes, cell has a cell membrane, plasma membrane, which forms the boundary of the cell, and it separates any cell from any other cell. So, you know, every house, every building has a boundary. So that boundary is a membrane. It's a complex membrane, which means it has protein, lipids, polysaccharides, a lot of different things. It also had cytoskeleton beneath it. So, but if we look closely about different kinds of lipids that are involved in forming the bilayers, we can just count them. And here are some of them listed, but actually there could be thousands of different lipids. And the interesting and exciting thing here is that if you move in the cell and you go from one membrane-bound organelle to other, you will see that the lipid composition is actually very different from organelle to organelle. And these lipids have shape and size. So they also diffuse laterally, and they also can rotate. They have rotational diffusion, lateral diffusion. They can flip. So they are very dynamic. They have a very dynamic and busy life like us, okay? Now, we can buy these lipids, and the moment we put them in water, they self-assemble and form a bilayer. Certain lipids form bilayer, not all of them. So if they form a bilayer, it's an equilibrium stable structure. And normally the thickness of the bilayer could be between 3 to 5 nanometer. So let's say it's 5 nanometer, and there are different various kind of interactions. As you know, any colloids suspended in water have different kinds of interactions. And these are some of the interactions that are also present with lipids, because these are also suspended in some kind of solvent. So there is an equilibrium area per head. And then another interesting aspect of the bilayer thickness, since it's very thin and the size of the cell is of the order of microns. So basically the bilayer is very thin, so it can deform very easily. And this is something very, very important when something from outside has to enter the cell or something from inside has to go out. So for example, like I gave an analogy with the boundary of any compartment. So anything that has to come in, it has to cross the membrane, and anything has to go out, it has to cross the membrane, whether it's outside, inside cell, or whether it's inside, outside organelles. So the membranes are actually very important. And what I plan to do in the lab here is actually to isolate the processes that involves biomembranes in the active as well as passive states, and try to create them in the lab in order to understand their function. So when we prepare such compartments, which are of the size of the cell, so on the left side, you see this, it looks like some bubbles, but actually these are membrane compartments, like of the size of the cell, as you can see from the scale bar. And they are kind of stuck. That's why you see them like that. So this is how it looks when we prepare it in the sample chamber. Okay, and this is a fluorescence microscopy picture. And if I take a cross section and if I want to draw a schematic, then basically the lipids are arranged in the bilayer fashion and they are closed in order to not to expose the edges to the water due to hydrophobic interactions. So because the hydrophobic part of the lipids cannot form the hydrogen bond, whereas the heads can, so they prefer to form closed compartments. So we can form these compartments in the lab. Now there was another thing that we would like to do, which is what the Ramalinga Swamy grant allows me to do, is to reconstitute protein, transmembrane protein, sodium potassium ATPase in these compartments. So this will be my first project here at ISR to actually reconstitute these proteins. So we are getting the protein from my collaborator, Professor Cornelius, who is at Aarhus University. Actually, his PhD supervisor is the one who got the Nobel Prize for the discovery of the pump. So we collaborate with the lab and we get the pump initially just to get started. And later on, we plan to purify it right here at ISR. So we want to reconstitute these proteins in these compartments. And then we want to study how the proteins density and spatial distribution has anything to do with the membrane composition and membrane associated structure or composition or asymmetry or any property of membrane, if that can affect the protein function and its distribution. So as you can see, right-hand side, this is a published work with Professor Cornelius that I did in my postdoc. And here we could actually count how many proteins are there. So these bright objects are actually proteins in A. In B, this is immunolabeling, where we use antibodies to detect the proteins. And in the C, which is down, this is actually, you can see the height of the protein, part of the protein that is protruding outside the membrane. So we could actually quantify the orientation. We can quantify the spatial distribution of the protein in the membrane, and we can precisely tune the amount of protein that we put in. We can tune the phase of the membrane. We can tune the structure of the bilayer. So all of these things we can actually do in the lab. So how the biomembranes get remodeled in the presence or absence of the protein. So the way membranes can get remodeled if I change the two leaflet composition with respect to each other. So for example, I can call these two leaflet as outer and inner leaflet. And if I want to bring another lipid molecule in one leaflet compared to other, then in order to adjust the external foreign molecules, it can create curvature spontaneously, and that can lead to tubulation or buds formation. So this is the work which I have not started here yet, but this is something it is already established during my postdoc at the Max Planck Institute. And we see tubulation and formation of buds if we create these kind of leaflet compositional asymmetry. So D is actually an experimental data which is published in 2018, where we showed that, if we have two different concentration of the lipid in the two leaflets, then it can give rise to either inward pointing tubules or outward pointing, depending on what kind of asymmetry we create. By that I mean, if I have higher concentration inside or outside, and we can create these tubules. The E also is published, where we showed that, if we have a higher amount of protein in one of the leaflet, it can actually bend and create curvatures and form buds. In F, this is also something which is published, where we actually show that, we can have domains, which are the reason where the like-minded lipid like to get together and stay in the colonies, So they form domains, and the size of the domains is something one can tune in the lab. So we can change them from nanometers to micrometer, depending on the compositional mixture of the lipid that we use. So this is something which is published. All of this work that I show in this particular slide is slide 6 is published. But what the message here is at ISR, what we want to do is we want to use this already published result to learn about what the pump can do. That is not something which is published. So that is what my grant allows me to do. So this one, these were movies, but it will not play here. So I will now try to show you the movie. So what will happen if, okay, I can have a new share, it seems. So I can,
so maybe you can share your entire screen so the process becomes easier.
okay. So, so let's see. Yeah, so this is where I have a different amount of lipids inside and outside in the two leaflets, and you see this inward pointed tubes. So this is a passive system. This is not an active system, but we could create tubes and out of the membrane compartments which has no tube. So this was one example, and then so I hope it's visible, right? The screen, yeah. Okay. So
yes.
now, so we want to work with these kind of systems, and the active part comes when we use actually the transmembrane protein into the membrane compartments that are cell-like. So by cell-like, I mean we will use physiological conditions for the protein that are present in the cell. We will try to mimic the same lipid environment. We will try to mimic the size of the compartment. We will try to mimic the orientation of the protein which is in the cell. So we try to reconstitute the protein in the right orientation, and we want to study how the membrane composition and phase can affect the protein function. And that is the active part of the projects that I plan to execute here at ISR. So for that, I will use something called micromechanics. So one of the things is the fluctuation analysis. So where we actually quantify these fluctuations. So these are just Brownian motion. So for example, this is one movie that I will show you. So if I prepare these vesicles, then you know, they are just membrane compartments and they are suspended in a fluid. Now these fluctuations that you see, these are actually Brownian motion, because the solvent molecules are kicking the membrane and the membrane is kicking back, and then there are these fluctuations which we can see. Now if I want to draw these fluctuations, you know, then this is how it will look. So I will have fluctuations, and then by quantifying the fluctuations, I can actually say a lot about membrane composition because if I change the composition, if I change the flexibility, rigidity, then the fluctuations, the amplitude of these fluctuations will change. And then if I look at the fluctuations at two different points on the same compartment, or if I look at the same point with respect to different time scales, so I can look at correlations, and it tells me something about the dynamics of the processes that are going on in the membrane. So for example, if I have an active process going on in the membrane, if there are membrane associated proteins, then the time scales of the functions of the protein can be extracted by looking at the time correlations of these fluctuations. So this is what we plan to do, and we have already have a microscope thanks to ISR. I'm very grateful for them to give me the funding to buy a very high-end microscope where we want to do this. The other technique is the micropipette aspiration technique, where we actually now, since we have these fluctuations, so we can quantify the amplitude of this fluctuation. The next thing we want to do is actually to create tension to this membrane. So for example, what I mean is, for example, so what I will take a capillary, that's what is a micropipette, and I have these juvies, and then I'm going to aspirate them in the pipette. And when I'm aspirating, I'm actually creating tension on the membrane compartment. And that tension, how much tension I can create, it depends on the membrane composition, it depends on the membrane phase, it depends on the active and passive processes in the membrane. So then I can quantify the mechanical property of the membrane, such as, you know, for example, I can quantify the tension, I can quantify the bending rigidity, stretching elasticity. Then I can quantify, for example, spontaneous tension. I can quantify if there is a conformational chain order of the acyl chain, if it is different. I can quantify different preference for the different molecules, whether they have preference to get partitioned in the high curvature region or low curvature region. So curvature sorting and things like that. one could quantify by doing this experiment. So this is another technique that we will have here at ISR. And this is one of the recent publications with my affiliation here at ISR, where I contributed actually to aspirate giant plasma membrane vesicles, which are like vesicles derived from the cell. And we, if it is aspirated, we see that, you know, the blebs, so-called blebs or giant plasma membrane vesicles, if they have inner pointing tubules, then they show a slope. So relative area change is, so let's say I have these fluctuations, and if I stretch it, you know, the area that you see in the stored in the fluctuation is different from the area projected in the pipette. So that's how you can define a relative area change. And if I plot the tension versus the relative area change, then the slope tells me a little bit about the modulus, the stretching modulus. And you can see here already that if I aspirate a cell, or if I aspirate a bleb with tubes, and if I aspirate a bleb without tube, then the slope is very different, which means that even when we extract the plasma membrane blebs from the cell, it can behave very differently. It can be very stiff, it can be very flexible, depending on what goes inside the membrane. So we have also tried to find out that, and we have tried to label the membrane before extraction, after extraction. We do see tubules inside, and then we also see a kind of compositional rearrangement of the lipids in the tube and in the giant vesicle. So which means there is a complete compositional heterogeneity at the high curvature regions, which are the tubule inside the bleb and on the membrane vesicle. So there is a heterogeneity in the composition, there is complete heterogeneity of the curvature, and of course there is a complete difference of the stiffness or the flexibility of different parts. And by doing these micromechanical experiment, we can quantify a lot of the physical quantities. So this is what we also plan to do here. Then coming back to the pump. So the pump actually transports sodium and potassium ions, and it actually is responsible for maintaining the resting potential of the cell, which is the basis of any nerve potential, right? So anything that has to communicate, the sodium potassium ATPase is one of the most important pump, and it actually takes about 70% of the ATP in the brain. So this is what we get in the beginning from Professor Cornelius, and the Ramalingaswamy grant allows me to do that. And what we plan to do actually is to reconstitute this pump in these compartments, and then to look at how the pump behavior is affected by the membrane composition and vice versa. So this is again published, my published work with Professor Cornelius in 2017, where we actually already showed that, you know, depending on what composition of the membrane I take, I will have different distribution of the protein and different function. So A is where I label the protein, the B is just, you know, orientation of the protein, and C is the experimental result in single and two-phase membrane. And you can already see that the bright spots are distributed in a very different way. So it can be homogeneous or heterogeneous depending on the membrane phase.
So you have just like 2 or 3 minutes.
Okay, thank you. So, so the aim is to build synthetic cell in the lab. And so these are already published, some of my published work. So I have the right expertise to create these compartments, to create budding tubulation. I have the right expertise to you know, study how a compartment can divide. So this was one movie I want to show you. So here we showed, you know, like if we increase, so these were like a single compartment, and then we could divide the single compartment into 2 separate compartments. And this is published in Nature Communication during my postdoc work at Max Planck Institute. So we want to use all of these knowledge that I have to create synthetic cell and to create shape transformation and to create compartmental division. And this has a lot of significance in active processes and passive processes that are occurring in the cell, especially for, you know, if we want to create a cell in the lab. These are important, and we are able to study the physics of all this, because the function of how we create it, how we stabilize these shapes, and how we introduce or drive these kind of processes is actually one can understand it by the principles of soft matter physics. And I'm a physicist, so I plan to do all of this. So lab status is that we are hiring right now. I have a postdoc, but we are hiring the students. So ISR also allows me to have a co-supervision of any student in any institute of the national importance in India. So you are very welcome to write to us. We have a microscope, ion microscope, and we plan to work with the active pump, transmembrane ion pump. And yes, so thank you very much for your attention, and I will be available for the questions.
Thank you, Dr. Tripta. Yeah, so the floor is open for question. Yes, Bibu, you can ask your question.
Yeah, hi. It's a nice stuff. I have a couple of questions. Maybe I'll just ask both of them. For these blebs, when you extracted them from the cell, so depending upon the process of extraction, you can have different sort of kind of membrane composition, isn't it? So, what was the process of extracting these blebs, GPMBs? Is a standard osmotic
This
swelling?
was no. This is with treatment with this NEM.
Ah, okay. So then my question is that, do you see some, for example, if you have a reconstituted membrane, I mean, the kind of fluctuation you see, and if you have a GPMB and the kind of fluctuation you see, is that very vastly different?
Yeah, they are different. One example you can see here that, so GPMB here, blue dots are like, if I take vesicles without any tubes or anything, then you will get something like what the blue one is showing, blue GPMB. So they have some stretching elasticity, which comes in millinewton per meter. As you know, that if we increase the tension beyond 1 millinewton per meter, they will rupture. But if we have these GPMVs that we extract with the tubules and with the cell, if we do that, so this is what we call super elastic objects. So they don't rupture so easily. So this is the latest publication we have from my side, where we showed that they actually behave differently. They are not the same.
Just if I'm allowed, just second question. So this regarding this pump. So I mean, is it already a kind of evident, or is it already kind of published about this affinity of these pumps towards the various domains of this your membrane? Because I presume you are going to integrate them in the GUVs with differential compositions.
Yes.
So do you have already some idea about about the affinity of these pumps for, let's say, LOLD domains or some domains with higher line tensions? So is there some sort of evidence already existing?
Yes. So what we know from the previous publication, so for example, this one is that, this pump, if we look at the structure of the pump, if we go to the molecular level and look at the molecular structure, we will find, as you know, like it's a transmembrane protein, so it has a hydrophobic part and it has a part which is not inside the membrane. So its hydrophobic thickness of the protein has to cooperate with the hydrophobic thickness of the bilayer in which we are going to incorporate. So there has to be a hydrophobic mismatch, right? Or match.
Yes.
Match, not mismatch. So it definitely, we have already shown that, the activity of the protein depends on the lipid bilayer composition in which we put, and that has something to do with the hydrophobic thickness of this protein. So we have already shown that if we put it in a membrane which has a single phase, which means that it has no domains, then it is homogeneously distributed. But the moment we put it in the phase with the domain boundaries, it has a preference to go at the boundaries, and that is because something to do with its hydrophobic thickness compared to the bilayer hydrophobic thickness. So yes.
And sorry, just to an extension, a quick extension. So if you have a mixed composition and then you incorporate these pumps, do you expect some phase separation? Like will they create the domain purely because of this hydrophobic matching? Will they kind of coagulate and then have a domains by themselves?
Yes, so if you look at this paper, Nature Protocol, that is published in 2017, we actually showed that they stabilize small scale domains.
Okay.
So we have shown that already, but that was a passive state. So now what we want to do here at ISR is actually to look at what happened in the active state.
Okay. Yeah. Thanks a lot.
Thank you.
Surrender, you can ask your question.
Yeah, okay. Excellent talk, Tripta. So I was just looking at your video that you are showing for the fluctuations.
Yeah.
May I ask, like, how did you collected this? Like, how are these so stable in that position? Were they absorbed on a surface or something?
No, it should not be absorbed on a surface, because otherwise it has another contribution, no, from the surface.
Exactly.
They are just free floating in the solution.
So I only see fluctuation.
Yeah.
There is no, like a trans. Yeah, exactly.
No, it will drift with time. So I'm playing it very slow. It will drift with time, and as long as we track it, it should be fine. I mean, as long as we track it, so there is. It is not. It is a free-standing compartment. It is not held by anything, and we are just looking at fluctuations, and then we just look it in the microscope. We record it, the time series, and of course, if you see carefully, it has already drifted a little bit. So of course, it will drift. It does.
Okay. Yeah. So then you basically what you do is like you get these fluctuations, and then you, like, for example, use a capillary wave model or something, and then try to get the tension. Is that how you do it, or?
No, so then what we do is so this is a spherical compartment, quasi-spherical compartment, and then we have a model where we model the shape of the GUV in terms of spherical harmonics, and then we go to the Fourier domain and we look at the amplitude fluctuations, and to characterize the fluctuations in the height of the membrane from a spherical geometry. So that's what we do.
Okay. Yeah. Okay.
Thank you.
Okay. Thanks.
So we have a time for one quick question. If not, we can then we can thank the speaker. So thank you, Dr. Tripta, for this beautiful talk. So we'll move on to our next speaker. So Bibu Ranjan Sarangi. So he did his MSc from in physics from Utkal University, Bhubaneswar, and then he did his PhD from RRI Bangalore in 2011. And then he did a couple of postdocs, one in Institute of Curie, Paris, France, and then another Institute Jacques Monod, Paris, France. So he's interested in mechanosensing in living systems. So yeah, so floor is all yours, Bibu.
So my screen is visible and I'm audible?
Yes, you are audible and visible. Yes.
Perfect. So thanks a lot, organizers, for having me here for this wonderful gathering to share some of the research works which are like a mix of some of the previous work and some continuation, which are the activities which are going on in our lab, which has almost just started. Thanks to the pandemic, the start is delayed, so we'll still kind of hoping to get it functional as quickly as possible. So some preliminary activities have already started. So yeah. So I'm Bibu, I'm from IIT Palakkad. So bit of advertisement. So our institute is coming up. It's a 3G IIT, so which means we are in the construction phase. Everything, labs, buildings, people. So everything is in a growing phase, and we are nestled in a beautiful setting just below the Western Ghats. So when the pandemic gets over, all of you are welcome to visit our institute and have a beautiful time with science and nature both. At IIT Palakkad, we have established a interdisciplinary lab, which we call as Physical and Chemical Biology Lab. And we are suitably funded by the institute itself, IIT Palakkad. I also have my personal grant from SUB so that we can establish a some sort of a functional lab with imaging facilities, cultural facilities, and biochemical characterization, as well as confocal microscopes and so on and so forth. Currently, I have two PhD students, Shiv Krishna and Indrajit, and there are a couple of master students who are working with me right now, Olivia and Niharika. So the kind of work we are kind of looking at in our lab, I mean, we look at 3D culture models, essentially a collection of cells in a confined or unconfined geometries, and ask questions like what sort of effects of pressure, what sort of biological and biophysical changes comes about when you apply confinement pressure to these cellular aggregates. then it has quite a good relevance to the cancer progression, where you can imagine this kind of a mimicking a tumor growth inside your body. So this is where the students Sevi Krishna and Yarika Maji are working on. They're trying to kind of make a different kind of 3D culture model, like freely going and different sort of cellular aggregates, and trying to study the velocity profiles and then using various biophysical techniques. The another project, which is again a continuation of what I did in e-SMYIM in Paris. This was regarding this dynamics of cell adhesions. So we look at cellular adhesions. I will go more in detail into this particular one, and we ask questions like what sort of dynamics the adhesion follows when it forms and when it disassembles. And that is the work of Indrajit Bhattacharya, who is working currently on this, who is trying to prepare different functionalized substrates and putting shells on them and trying to observe how these adhesions evolve. And in this, we have collaborations with my postdoc supervisor, Benoit Ladu from e-SMYIM Paris. I am also starting to have a collaboration with Rumi there from ISER Kolkata, who does simulations and who does modeling for these adhesion structures. And then we also, in another project, we also look at membrane antimicrobial peptide interactions. The idea is to look at, as already Tripta pointed out, the giant uniluminal vesicles. I don't have to introduce this particular system. So we have basically lipid vesicles, and then what we are trying to do is we're trying to understand the dynamics of the pores. Essentially, when you put some peptide molecules like antimicrobial peptides, they induce pores. Again, the mechanism of pore formation is multiple. There are multiple pathways where the pore formation can happen. So, but then we are interested in very specific AMPs, which are actually used for these food preservations, and then trying to look at the dynamics of the pore formation using some imaging techniques and other complementary techniques. And here I'm getting help from Shobhan Lal Das from IIT Palakkad, as well as Bharat Kulkarni from Central Universities, Karnataka. So today I'm kind of going to talk about one particular aspect because of time constraint. So I'll be mostly focusing my talk on the adhesion dynamics. So we'll be talking about cellular adhesions. I'll just give a brief overview of what cellular adhesion look like, and then I'll finally focus on the current work, which is kind of we are writing it up on the adhesion dynamics particularly. So I'll also show you what are some of little bit of my previous work where we talk about the force measurements at the adhesion structures. Okay, so the big questions which we are asking is how do cells sense and response mechanical cues from the environment? So when I say mechanical cues, so you can have cells on either substrate or inside your body or inside or inside some kind of a reconstituted matrix. So the question is, I mean, how do they sense the mechanical kind of stimuli from the environments? And the mechanical stimuli can be of different form. It can be substrate topography. It can be the mechanics of the substrate, for example, the rigidity. It can be a confinement pressure. I mean, if you just confine them in either 2D or 3D confinement, and then ask questions like what should be the confinement pressure, how confinement pressure will affect the biological activities or biological processes inside the cell. And these kind of mechanical stimuli can manifest in a different sort of, you can have different sort of manifestations in the cellular level. We can have changes in the cell mechanics. We can have changes in the cell morphology. There are many biological processes which can also change, and in the long term, it can also affect the disease progressions. And this the process which links these two is known as mechanosensing. I mean, the name is quite evident. It just senses the mechanical cues and then how it does. Obviously, as a physicist, we are interested in the dimensionality of this process and the length scales of this process, whether it is happening at the molecular level or whether it is happening. So, or whether it is happening, at the level of individual cells or at the level of individual aggregates. So that the length scale I'm talking about, it also matters what dimensions you're talking about. I mean, whether you are looking at cells plated on a 2D substrates, or you are looking at cells which are in a collection of cells which are in a form of an aggregate. So all these things matter in when you talk about the mechanisms. I'll just focus on one particular aspect of it. So the way the cells do mechanical sensing, you have some adhesion joints, some adhesion structures. So you have some sort of a mediator between you and the substrate, or ECM. You can call it the extracellular matrix. So these are adhesion structures. There are some complex protein assemblies which are which kind of anchors the cell to the substrate or to the ECM in let's say in a network in your body or in a kind of in a gel. These are very complex structures involving lots of proteins, and then it is the hierarchy also is kind of quite well studied. I mean, people have these were kind of the discoveries goes way back to 1970s, where people looked at the ECM structure. They found electron-rich domains, and then they kind of called it as an adhesion flag. And then subsequently, with the advent of high-resolution microscopies, people have gone on to image these focal adhesions in great detail. And then, started to look at what these adhesion structures look like, their morphology, their compositions, and they seems to have, kind of evolved in a more kind of comprehensive understanding about these adhesion structures. They are influenced in different processes. They are very important in maintaining the tissue integrities, the cell organization, and of course, directed cell migrations. The directed cell migration, when I say this is also again very important for your wound healing, even the growth, the development for a lot of biological processes. So as you can see, I mean, these adhesion structures are quite crucial if you try to understand the system. Okay, so I mean, again, I mean, these are quite complex structures. This is an active system, and then this is with a lot of components. This slide is just not to confuse you. This is just to show that these are the kind of proteins identified so far, which are either directly involved, which are intrinsic components, or they are kind of associated components. I mean, more than hundreds of proteins in these small adhesion plaques, which are typically of the dimension of 1 or 2 microns. Okay, and so it's essentially difficult things to really mark. But what people do, they pick up 1 or 2 proteins and try to see their functions in this kind of. So they study these things in isolations, and because it's very difficult to kind of look at everything in coordinations. So how do they look like in a cell? This is what I took an image in a confocal microscope using a focal adhesion protein known as vinculin. And the red things, what you see is the actin filaments, which already Nitin has already talked about a little bit about that. And then the green thing which you see is the adhesion joints. So these are the focal adhesions. And as you can see, each focal adhesions has connection to the actin stress fibers or actin filament bundles of actin filaments, and then these are the anchor points. Okay, this is how you observe them using either fluorescence or a confocal microscope. You can do much better. You can do some. You can use some super resolution microscopy to again understand the structures. Again, I mean, people have done comprehensive amount of work understanding the architecture of these focal adhesions. We may this name may trigger some alarm there, because this is the Nobel Prize winner for super resolution microscopy. So he also kind of looked at this focal adhesion in super resolution microscopy, looking at the compositional homogeneity. And then Clara Waterman's group also, they looked at using super resolution the hierarchy, the architecture of this focal adhesion in the Z direction. So the blue ones, as you see, are the actin filaments. So as you can see, there are transmembrane proteins connected to the ECM, and then inside the cell you have this actin cytoskeleton, which carries this whatever mechanism sensing the focal adhesion does to the actin cytoskeleton network. More than that, we have also studied the force which is exerted at the site of these adhesions. I mean, both the normal as well as the shear forces. And they have shown how what are the homogeneity in the force distribution along these focal adhesion lines. I mean, you can see this is actually end-to-end distance of the focal adhesion, and as you can see, the shear force is maximum at the middle of the focal adhesion, whereas the normal forces are have homogeneity, with respect to the center of the adhesions. And we also kind of worked on it on this force measurements on the adhesion side. So what we did actually during my stint at the IGM Paris, so what we did actually, we took these micropillars, we put the cells on it, and then the cells will adhere to these micropillars. And when they kind of apply exerted force, then we have this kind of a bending of the micropillars. And if you are careful enough, we can actually measure these deflections of the micropillar, use some simple elastic theory to kind of map these forces, to kind of look at how much force is exerted by this one single adhesion plaque. And then more than that, what you can do, you can also integrate some of the force sensors inside the cell, like FRET sensors. I mean, people who work on microscopy, they will particularly understand this term FRET. This is a force resonance energy transfer. It's microscopic techniques where you use two fluorescent dyes, and then you kind of illuminate, you can excite one and then look at the fluorescence of both the dyes. And because of a non-radiative transition between them, you can, which is sharply depending upon the the distance between these two, you can actually figure out the distance between these two proteins. Now, if you can put a linker between them, so the extension can be mapped by the FRET intensities, and that is how we did it using some FRET sensors inside the cell. And what we reported is that there is an inhomogeneity in the protein tensions. So the FRET will report the tensions inside the protein, whereas the pillar will report the forces outside the cell. So we kind of established that there is a synchronization between the force which is exerted from the substrate and the intramolecular tensions which is exerted, which is experienced by the protein. Okay, and that protein is inside the focal adhesions. And then you can go on further, look at the adhesion structures, each adhesion structures from the end to end, and look at how the tension is distributed. And there also you can find the inhomogeneity, and you can correlate them with the morphology of the focal adhesions. Anyway, I mean, the details can be found out in this paper. Now, what more we can do with it? Now, the question was, this is actually gives a passive picture. So you have an adhesion structure, it is exerting a force, and you are mapping the forces. So what we now kind of went and do more and more on this is to look at what happens when you are asking question about the dynamics. So what sort of the force signatures you will get if you look at the forces, how it evolves during the assembly and disassembly process. So I'll just go a little bit more into this. But before that, let me play this video. So what you see here is actually a cell which is put on some sort of a micropillars. I mean, these are PDMS micropillars. I'm not really going into the details of these techniques because in the interest of time. So all I can say is that you have some kind of bed of microneedles, and on top of that you have a cell which is kind of migrating and which is kind of doing all sort of motions. And now when it does it, I mean, it tries to kind of deflect the micropillars. Then you can map both the proteins. So you can see the green one here is essentially the actins. The white one, if you see the right side, is actually the focal adhesion proteins, and the red one here is the micropillars. So you can map all those things dynamically and ask questions. First question you can ask, what is the force being exerted at the adhesion sites? The second question you can ask, what are the protein composition, how the protein composition is changing during the process of assembly and disassembly. Now, when I say assembly and disassembly, so I mean, imagine a cell is moving. So when the cell is moving, it has to kind of form new adhesion joints at the front end, and it has to retract from the back end by disassembling these adhesions. And these are very dynamic processes. I mean, then the trigger, and we can go talk more and more on details about what triggers it and so on and so forth. But let's not concentrate on those kind of triggering processes. Rather, let's just ask question: what happens when it retracts? So I mean, then you can you just disassemble the adhesions here, and on the right side, on the front end, you assemble the adhesions. So these are the zoomed pictures of the disassembly points. And these yellow things, what you see is the force vectors superimposed on these pictures. Then you can look more details about this assembly and disassembly process. The first thing, I mean, you can ask questions: what are the times? Because you are studying the dynamics. So probably the rudimentary thing to ask is what sort of time scales that are involved in these two processes. So as you can see, the left side, it gives you the time scales of an assembly. The time scales running in synchronization with both, which means you can see the assembly process. There's pretty long process. I mean, typically of the order of 10 to 20 minutes. Just to a word of caution, this depends upon the cell type and the substrate and the kind of substrate mechanics as well. But for this particular case, I'm talking about this assembly process typically takes of the order of 10 to 20 minutes. Whereas the disassembly process, as you can see the right side, it is a snap. I mean, it just disassembles within a couple of minutes, let's say 2-3 minutes. So there is a huge difference between how the construction happens, how the destruction happens. Okay, so it's not exactly the reverse process. And more than that, what you see is the way the disassembly happens. I mean, this picture tells you from which part the disassembly starts happening, whether from the cell center or from the cell edge. Counterintuitively, the disassembly starts happening from the. You decrease the protein concentration from the cell side first, and then finally you break the patch which is at the far end of the adhesions. Okay, so then the time of the measurement part comes. I mean, then you look at the measurement. This is one single trace of the evolution of different parameters for both assembly and disassembly process. So the left side, what you can see is the three curves representing the area. I mean, the patch area, the intensity, the protein intensity, the protein concentration, which is which is given by the intensity of the fluorescence intensity, and then the pillar force. So as you can see, they just take some 20 to 30 minutes, and then they mature. Then you hit a saturation phase. Whereas if you look at the disassembly process from the saturation, it just has a step process. You kind of disassemble the patch all at once. You can do it in a high temporal resolution, and you can plot several traces of these curves, and then you can kind of try to understand it using various existing methodologies and some, modeling.
So Vibhu, you have another 4 minutes or something like that.
Okay. Sorry, I think is my screen visible? Somehow it's not.
It's visible. It's visible.
Okay. Okay, so just to tell you like what are the existing kind of people, how do people understand about these adhesive interactions? So essentially there are two formalisms with which people try to understand this. One is this slip and the catch bond formalism. So essentially when you apply force, if the bond lifetime actually is a force dependent mechanism, and if you reduce the lifetime of the bond when you apply force, then you call it the slip mechanism. Whereas if you increase to certain threshold value when you apply force, then you call it a catch bond analysis. And what is currently the current understanding for this adhesion patches are these, you have both these kind of mechanism existing in the focal adhesion structures. So, but however, one can also understand, evolve a macroscopic understanding of this process by what we did actually. I mean, instead of looking at these microscopic details, this part again, I mean, is being done with Rumi there from ISO Kolkata, who is doing a simulation based on this catch and slip mechanism and try to kind of get a time scales of this disassembly and assembly process. In addition, we also have developed a kind of these are models that are already existing in gels, poroelastic models. So we took those existing poroelastic models, I mean, with Horacio Lopez from University in Madrid. So what we did actually, we tried to kind of model these time scales of assembly and disassembly. And now let me again, I'm not going into details of this theory and but we can discuss more if you when we talk about it, or maybe in the email communications if you are interested. So the idea is the following. I mean, you have a mesh with actin networks, and then you are kind of squeezing these fluids through this mesh, and then you're asking questions. What should be the typical time scales with which you can squeeze these liquids out? So when the cell is retracting, and then you have this thickness is getting squeezed, so they're applying a squeezing pressure on these liquids, and they try to escape through this mesh. And then with certain kind of theoretical basis, you can calculate a typical time scales, which comes out to be typically of the order of 10 to the plus 2 seconds for this liquid to squeeze out of these adhesion sites. And that's typically the time scales which we get, which fits quite well with whatever we get for the disassembly process. So the idea is that when the liquid gets out, so you reduce this protein concentration drastically, that kind of triggers this disassembly, and that is how you can see a kind of a strong decay in the adhesion forces when the disassembly happens. You can do more, which we are developing currently right now in the lab, is to study the geometry of this adhesion. So what we do is that we prepare these patterns with different. So these are surfaces printed with adhesive patches. I mean, these essentially you can use some PDMS stamping to create these patterns. So only these dots will offer you the adhesions. Rest of the part is passivated where the cells cannot adhere. And then you ask questions, what happens to the geometry of these retracting edges, because you are now giving some sort of a lattice, some sort of a pattern substrate for the cells to retract. Okay, so you can prepare with 4, 6, 8, 12 microns, and then now you kind of zoom into it and then ask questions. What exactly is the retracting edge doing? So in the left side, what you see is the geometry of the membrane, the cell membrane, when the disassembly is happening. You see a pretty regular shape around these patterns, whatever patterns you are offering. And in the right side, what you see is the cell which is kind of trying to move towards doing some assembly to do the migration. And you don't see the regular geometry what you observe in the disassembly point. And these curvatures are quite well correlated with the pattern geometry. Now, there are the existing formalism for this disassembly is that there is a strong role of microtubules, which kind of plays an important part in signaling these disassembly processes. And the way the microtubule carry the signal is quite a thing to understand. So what we kind of think of is that this geometry can guide these microtubules to kind of carry the signaling to this disassembly patches, the patches where the disassembly is happening. And to understand that, we kind of looked at the microtubules and looked at the activities when the disassembly is happening. And there are ample evidences which suggest that the microtubules are being guided by the geometries, and then they kind of have a higher activities when the disassembly is happening. These are EB3 tagged microtubules, which means you are tagging only the end part of the microtubules. The dots, what you see there, is the kind of the microtubules which are getting polymerized at the end. So this is the EB3, which is only tagging the end of the microtubules. So then there are other kind of biological works which to complement this sort of understanding. How much time do we have? Can we go to some other thing or?
No, you are almost out of time.
Fine. So then I'll wrap it up. I thought of giving also another flavor of what other things like the gradient, rigidity, gradient substrate, but that's okay. So okay. So then I can summarize this part. Then I will. So what we actually essentially try to do is try to understand the disassembly processes, and we kind of have evidences to suggest that the disassembly process follows a distinctive force signatures. And the geometry seems to be very important in this disassembly structures, and we kind of using simulations as well as some existing models. We kind of try to see how theory can complement our experimental observations. Okay, I think that's it then. I will not move to the other part of the direct cell migration. I'll stop here. Yeah, thanks a lot.
Thank you, Vibhu. Thanks for this nice talk. Okay, so we have a question from Tapan.
So hi, Vibhu.
Hi.
Yeah. So I was wondering, what is happening to the bottom of the cells? Is there any kind of capillary effect coming from there? What is the weighting phenomena happening?
Okay, so the weighting phenomena, actually, I cannot really comment on how the weighting happens because there are membranes. So what actually we have only, so the attachment happens only at the adhesion sites. The other side, where the membranes actually touches, they don't adhere. So which means, you can think of it like they don't weight at all because they don't adhere.
Yeah, my question is actually, I understand that they don't adhere, but do they actually go down or they remain flat in the
so that's a kind of interesting thing. So people have looked at some of the things. So the adhesion patches, they're the slide. So which means on the other side, the other parts, which the membranes. I don't think they, at least I have not looked at them, but I don't think that they kind of, what you call, you are asking about whether they weight or they kind of, slide through.
Yeah, so supposing that the fluid or the membrane kind of weights, so they go down the pillars, then they might actually affect the growth in the front. Okay.
Okay. So for the pillar part, I can the pillar. Yes, if you're asking about the pillars, then I have documented evidences for that to answer your questions. For the continuous substrate, I don't have. But for pillar, yeah. So they can't go down because the substrates are totally passivated with PEG and all, which means it will totally prevent them to go down, or kind of, and also it's filled with kind of liquids. And the distance between these two pillars are typically of the order of 2 to 4 microns. You can change that also, which means very difficult for them to have a curvature and then go down and attach.
I see. Yeah. Okay. Yeah, thanks.
But just to continue there are, I mean, if you don't passivate well, they actually follow a pillar shape and they do really go down, and then that time they get stuck. They don't really move so much.
Right.
Yeah, that may actually answer your questions which you asked in the beginning. So if they go down, it will be very difficult for them to move around.
Right.
Yes.
Okay. Thanks.
Okay, Sunita.
Yeah, hi, Vivu. Very nice talk. So it's somewhat related to what Tapan was asking actually. So you showed this regular structure in the form of pillar. My question was, what prohibits your cell membranes actually to go down within the pillar spacing, and does this length scale affect the kind of assembly and disassembly processes that you were saying?
Yeah, actually it's a very interesting question. Yeah, so okay, first question is that they don't go down, as I already answered Tapan, that it is passivated, which means we intentionally prevent them to go down. Okay, that's the first question. But again, just to have a counter.
So sorry, Vibhu, I did not understood. So what do you mean by passivated? Like you?
So you coat them with some repelling polymers where the cells can just like peg or like some other polymers where then the cell doesn't have any adhesion joints there. So if they don't have adhesion joints, they just can't go down.
I see. Okay.
But then just to again have a counter argument. So sometimes when the passivation is not good, so the cell actually crawl through, and then you have they take the shape of the pillar and then they simply adhere to the pillar, and then you don't have any, because then you kind of don't have any data on this pillar bending and all. Then the cells don't migrate so much. Yes. So we don't really we passivate quite well. And your second question about.
Second question was, does the length scales of these pillars that you have on the substrate, does this affect the dynamics?
Yes. So there is a kind of two different kind of school of thoughts regarding this continuous versus discrete adhesions. Now, the people have done careful experiments looking at the like the percentage of adhesion areas where you kind of match with their continuous proliferation of what they would have done on a continuous substrate. And that kind of turns out to be typical of the order of 20% to 30%. I don't exactly remember the number now. Now, we always maintain that number in the sense you don't really make it so much discretized that you don't give them enough surface to adhere. So you maintain the pillar, the lattice size, the so-called lattice size so much is that they have ample size to adhere. Okay, that's the first thing. And if you change them, I mean, then you do affect all those assembly disassembly quite a lot. But what you saw in the last part, that was not done on pillar, that was done on continuous substrate, but with only adhesive printed structures. So you print these continuous substrates on these adhesive proteins. That's all. So you just print it on the continuous substrate.
Okay, yes. That's very interesting. Okay, thanks.
Yeah, thanks.
Okay, so if there are no more questions, let's thank Bibu for this nice talk. So the next speaker, or the last speaker of this session, is Dr. Tapan. He did his PhD from Physics Department, ISC Bangalore in 2013, and then he did like 3 postdocs in TU Berlin, Johannes Gutenberg University, and Max Planck Institute for Polymer Research in Mainz. And in 2019, he joined IISER Tirupati. And his research interests are mostly like physics of active matter, non-equilibrium statistical physics, and biological systems. So yeah, so floor is all yours, Tapan. So you are muted, but we can see your screen.
Yeah, sorry. So yeah.
Now we can hear you. Yes, now we can hear you.
Okay. Thanks a lot, Nitin. I mean, so how much time do I have actually?
So you have about 20 to 23 minutes for talk and like 7 minutes for interaction, something like that.
Okay. Okay, thanks. So, and I mean, first of all, I congratulate the organizers for actually arranging such a nice get together, and hopefully, as someone already suggested, I mean, so hopefully it will be like a physical meeting soon in the next years. So, I mean, so can you confirm, Nitin? I mean, so are you able to see my screen and my cursor both?
I can see it very well.
Okay.
Yes.
Okay. And are you? Can you see this thing? I mean, so this is. Can I?
Yeah, I can see the bottom and the top. Yes, I can see everything. Yeah, everything is visible.
But these buttons, like stops here, so I don't want. I want to get rid of them.
So even I don't know how to do that. So just pretend that they're not there.
Okay. Yeah. Okay. So yeah. So I mean, thanks for the introduction, and thanks I thank the organizer, especially Sunita Di and Dr. Ravi from IISER Tirupati for giving me the opportunity to speak. So I'll be talking about flagellated active particles in suspensions, and this talk is kind of an outlier of this of this session. I mean, so this will be a theoretical talk, full of equations. Very nice time to discuss the end of the day. Okay, so I mean, I don't want to scare, but I actually give a shock to all of you. So let's wake up if somebody is still sleeping. Okay, so let's start. I mean, I want to talk about active particles, especially in suspensions. And Nitin already has given a very nice and a very concrete definition of active particle. I don't want to do that. I mean, so I want to give a very sloppy definition that works for my talk. The definition is active particle is an object that moves by its own. I mean, that can self-propel without the presence of any external force pushing or pulling it. So in that sense, I mean, this bacteria, it's a real bacteria, is an active particle. It moves by itself. So it has a cell body which is fairly round and rigid. And it has a flagella behind the cell body, which is relatively flexible. And this is moving in a fluid. This is another example. It's a slightly complicated example. It's taken from our simulations. Here the cell body is elongated and flagella, there are more number of flagella. Okay, but nevertheless, both of them use the same mechanism to propel. I mean, the flagella pushes the fluid backwards. As a result, a reactionary force actually acts on the cell body that drives the cell body along that direction. So here is another example. The difference being that the flagella here is actually in front of the body. So rather than pushing the fluid, the flagella actually pulls the fluid towards itself and the whole thing moves. So when these objects move in fluid, they will disturb the fluid around them. So they will actually create these active flows. And for this type of particles, swimmers, we see that the fluid is actually pushed away, both in the forward and the backward direction. So these are called pushers. In the other example here, the fluid is actually pulled into the object, both in the forward and backward direction. These are called pullers. And these hydrodynamic flows actually play a very important role. I mean, if you imagine another swimmer nearby, the second swimmer will be affected by this kind of flows through something we call like hydrodynamic interactions. So why we are actually interested in this? I mean, so I picked up, without going into detail, I have picked up certain examples, okay, just to motivate you. So one example is that, I mean, if you consider these particles in a suspension, the suspension as a whole, I mean, the fluid plus the particles as a whole, they behave very surprisingly. So for example, there could be very unexpected stability of order, if there is any. There could be surprising viscoelasticity. There could be superfluidity. For example, here, I mean, so this graph also shown by Nitin. So here, this is a bacterial suspension. The viscosity, it is shown that it is actually goes to 0, okay, under certain conditions. That is actually very akin to the superfluidity, right? A similar analogous phenomena happens, so it can be actually analogous to the superconductivity and etc. So there are various, this kind of surprising phenomena happens. But instead of looking at the suspension as a whole, you can also look at the particles themselves. Okay, how do they actually move? And then you will see that there are lots of self-organized patterns, collective behaviors. This is again a bacterial suspension confinement, under confinement. And they spontaneously develop these collective flows, okay, so with different directions in different regions, for example. But these are systematic collective flows. So here is an example again of these are microswimmers, which are actually artificial, not living. Nevertheless, they are active, and these are in a suspension near a substrate. So these examples are taken from Ravi's lab at ICT, and he is actually managing various different shapes of these particles and various different conditions, activity, strength, and so on. And it turns out that these particles actually phase separate dynamically, or they form and break liquid crystalline order, they swirl, and many interesting phenomena is happening. So this is about just the particles, if you look at the particles. Then another third aspect is that, the particles offer novel responses. They give novel responses to external controls. So here's an example here, by switching on a light, these microswimmers can be actually focused to the axis of a channel. Another example here is just pointing with a laser pointer. The microswimmers are attracted to a point. In turn, they create such a flow in the vicinity with which you can actually trap a passive bead. Okay, they call it the hydrodynamic tweezer. So all these are very interesting phenomena that doesn't happen in a regular system. So that happens only in active particle suspension. And that's why we're interested in. And as you can see from, these are just only a handful of selected phenomena, but there are many more phenomena. It's really rich, okay, this system. And as I said, there are surprises, there are novel physics, and most of them actually are not well understood. So we know a lot, but we don't know a lot more. But what we know so far is that, in all these systems that I have picked up, the hydrodynamic interactions is really important. And especially the interplay of activity versus hydrodynamic interaction. So this is quite important in all this. So in our group, we actually try to explore these kind of systems at various length scales. Okay, this is one extreme limit where we consider really large systems using continuum limit, where we don't care about individual details. Okay, it's kind of blurred out. We just take the details at the large length scales. The other length scale here, so we just consider just one of the particles that would be here. So this particular particle is actually a bacteria, E. coli. As I said, it has a elongated cell body, and these are its flagella. It has multiple flagella, and the flagella are actually helical in shape. So we have a very realistic model for that, simulating that propulsion dynamics of this bacteria. And this is quite detailed in the sense that also it's expensive. So you cannot actually simulate a big suspension. So to bridge these two rings, we actually go to a third length scale, where we want to start from each particle like here, but we actually reduce the amount of information we have per particle, but we keep the minimal amount of information. And the idea is to simulate the large suspensions, like containing hundreds or thousands of them. Okay, that is the idea. So in this talk, actually, I'll talk about this work first, and then these two works already have been actually presented by my students in mini talks, but I'll still give some kind of background ideas at least. Okay, that's kind of the outline of my talk. Okay, so let's begin. So first, the E. coli thing. So this is a real, so these two movies are also shown by Amboris already in his mini talk. So this is a E. coli. So you can see it actually moves in straight path, and then sometimes it tumbles and it changes its direction. Okay, this one, for example, it changes direction and moves in a different direction. So that's called tumbling. So these are bacteria which are moving near a substrate, but not exactly touching. There are differences in the dynamics. The third one is an example where a bacteria actually, this is also from an experiment, by the way. So the bacteria approaches a substrate and gets trapped to it. After that, it actually keeps on traveling along the substrate. Okay, so in most of these examples, the flagella is not well probed. It's a challenge to probe the flagella. Actually, there are very handful of groups throughout the world who can actually visualize flagella during the locomotion. As a result, there are many open questions, related to flagellar dynamics. So this is where we actually want to contribute. So there are open questions, for example, what is the role of flagellar dynamics in tumbling? Okay, I'll come to that point soon. What is the effect of shear flows, for example, which you cannot avoid in real systems? And what is the mechanism of such a surface entrapment? So by the way, this phenomena is actually the pre-stage that leads to the biofilm formation. So that means that this is actually I don't know how to remove that there. So this is actually very, very important in biomedical and biotechnological applications. And the process of entrapment is actually is an open question now. It's there are contradictory results that have been published in the literature. But what we know is that there is a complex interplay going on between hydrodynamic interaction, flagellar dynamics, which is not well understood so far, and also shear flow and other things. So our group is actually trying to understand these aspects using simulations where we can actually really probe the flagellar dynamics. So this is our model in a nutshell. So this is a cell body. We keep track of, so this is, we have just shown one flagella here. There are many. So each flagella is actually rotated by a motor, biological motor that actually is inside the cell body. So we keep track of discrete points along the center line of the flagella. These are RIs. And also because the flagella has a thickness, we can also twist it about the center line. These are phi. So if we update RI and phi, then basically we update the flagella. So by the way, we have also hydrodynamic interaction between different flagella and steric interaction and so on. So these are the equation of motion for this Ri and phi. So these are forces and torques felt by the flagella at each point. So for example, one part of the forces and torques are the elastic forces and torques. They can be derived from an elastic free energy, which looks like that. Okay, you don't have to follow everything, but the summary I'm just trying to convey. So this free energy will be actually minimized by the flagella throughout its length. If it happens that the minimization happens corresponding to this well throughout the length, then the flagella will be in this form, which is called a normal form. However, in certain situations, there could be local transition from one minima to another happening at the local region. And that point, there will be a shape change from this blue to the green portion. Okay, so all these things can be captured with our model. And this transition is called by the polymorphic transition in the flagella. So using all these algorithms, if we put together, we generated this run, for example, and this is a run where you see that flagella are actually coming to a bundle. So due to lack of time, I'm not presenting the entire thing, but we just analyze this bundling process. One of the very first instances where the cell body is actually allowed to move. During a locomotion, the bundling process was studied, and already we actually gave the mechanism and showed that, gave the mechanism that actually contrasts the ideas that were actually founded before our work. But those works were based on bundling dynamics for flagella, which are actually attached to static bacteria. Okay, this is the transition that I was talking about. That happens when the motor that is rotating the bacteria in a reverse sense. That's when the transition happens. So this is a transition happening. One example. We also studied this very systematically, the potential landscape, and I'm skipping that entire thing just to give you a flavor that using these ideas, okay, so we generated a tumbling event, and this is the tumbling event. So you can see that both the flagella are in the blue phase now, but one of them will actually turn to green. And that's where the cell is now tumbling, it's not translating anymore. The green phase will actually go to red phase. And finally, the red phase will come back to blue phase. Okay, there is a series of transitions that is happening. And finally, the cell body will pick up one new direction and it will move this way. Initially, it was moving that way. So that's the tumbling event that we have simulated. And this is the tumbling angle that is the change in direction. We actually studied it quite carefully and still studying it actually. So what we did, we allowed the tumbling events by allowing different sequence of transitions. This is the experimentally observed sequence that you have seen there in the movie, but we all allowed other sequences as well. And we allowed the points of attachment of the flagella to change over the cell body. And we found the statistics of such tumbling events. And our initial data shows that the experimentally observed transition, sequence of transition, gives the most efficient bounding. Okay. However, this is just a preliminary statistics. Statistics is so far very poor, so I would not actually put my head on it. So currently, my PhD student Vignesh, he is actually accumulating more and more statistics. He is also allowing 4 flagella, 5 flagella cases. And he's also studying the tumbling, this polymorphism in a greater scale. He has a mini talk tomorrow at 12 p.m. If you are interested, you can attend this talk. So, I mean, with this kind of tools, we are actually heading towards actually studying the cell surface interactions that I have actually advertised earlier. And this work will be done in collaboration with Vignesh and our partner group in TU Berlin. Okay, so that's kind of that thing. I mean, so now the other 2 work actually mostly was spoken by my students already. So what I will do, I'll actually give the background leading to that works. Okay, so here we want to model e-SMYIM to actually generate the hydrodynamic interactions to an accurate level so that we can simulate a large suspension. So we need the disturbance around e-SMYIM to get the hydrodynamic interaction. So the minimal model that you can think of is that is the force dipole, okay, equal and opposite forces acting on the fluid. So this force, for example, can mimic the forces by the flagella on the fluid. This force mimics the force that the cell body is applying to the fluid as it moves. Okay, so this model will actually create the flow field, which is actually accurate if you go far away from this object. If you go far away from the object, this cell body will be like a point-like object, which will be like this point force. But as you come nearer, you will begin to see the extended nature of the cell body. So we thought that we should actually, instead of making it a point force, we should actually apply that to a sphere. Okay, this is the cell body, and for simplicity, we consider it a spherical cell body. And this force will be ultimately transferred to the fluid through the surface. So that's our model. So once we had the model, we actually kind of studied it. Okay, so we can do various calculations. Calculations are usually messy, as it typically is for fluid dynamic calculations, but I'll actually try to give the essence. So we solved the model for the cell propulsion velocity. So this is plotted here. Okay, so what is happening here? Suppose this force, this is the flagella force. Suppose that force is far away. Then effectively, this is an isolated passive sphere dragged by a point force, right? So indeed, its velocity is like that of an isolated sphere dragged by a point force. But as you bring the force, the flagella force closer and closer, the flow field created by that force will actually try to slow down, because that will act on the surface and it will try to slow down, and that's why the cell propulsion velocity decreases. And the cell propulsion velocity has a nice and small simple expression that depends upon the geometry of the model. So this is, for example, the radius of the. So once we have the cell propulsion velocity, we can actually study the flow field. That is the main interest, right? And so we can actually have the flow field.
Tapan, you have just like 4 minutes, something like that.
Okay, we'll try to wind up. Okay.
Yes, yeah.
Okay, so the flow field has various contributions. Okay, so for example, the translating sphere will create flow field. The point force will help also its flow field. So these are very easy to calculate. A difficult part is that the point force, the flow field due to that will be reflected off the surface. That is difficult. Okay, this is non-trivial calculation, but we can get help from method of images. So typically we have to, actually what we have to do, we have to solve for the velocity field here, provided that the velocity field is actually 0 here. We have to solve Stokes equation to do that. Interestingly, the Stokes equation has a nice analogy with the electrostatic equation, that is the Poisson's equation. In fact, the green function of these 2 equations are very similar, apart from the tensorial details. So then there is a one-to-one correspondence of this model, of this problem with this image problem that we have all studied. So namely, there is a charge in front of a conducting sphere, and you have to calculate the potential in this region, provided the potential goes to 0 on this surface. Very similar to this condition, right? So this was solved by introducing an image charge on inside this sphere. Okay, and we say that the effect of this sphere is actually kind of mimicked by the image charge. The same thing is happening. To get the reflected flow, we have to find the image of this object. And interestingly, the image actually is very similarly located as compared to this one. So only thing is that the image is like kind of slightly complicated. It's a system of images. These are objects that create flow field. Okay, each of these objects has their own flow field like shown here. So if you add all this flow field, then you get the reflected flow field. And if you add all these three, you get the total flow field of the swimmer. And that flow field was shown here very nicely, actually explained by Direk in his mini talk. So we get nice and convincing actually comparison of the experimentally observed thing. And then just since we had the flow field, now we can place another swimmer there and we can calculate the hydrodynamic interaction. So that is actually embedded in these matrices. Information about hydrodynamic interaction. And these are messy, but we had calculated. And then Direk is now implementing them in simulations to study their dynamics. For example, here is Stokesian dynamic simulation of 3 swimmers. You can see that they focus and then they go away. But it very much depends upon the initial condition. For example, if one of the swimmers actually precedes, the focusing is too sharp, okay, much sharper than there. So Direk has observed that, I mean, so by observing the fluid flow around them, and he kind of concluded that the extent of the cell body is actually important in some of the observations. So this part I actually skipped. This is because of lack of time. So Direk, means he said in his talk, he's interested in dense suspensions. So as he argued, I mean, in dense suspensions, very likely that the flagella do not have space to be straight. Okay, in a crowded environment, the flagella has to be bent. I mean, it is very plausible. So then we allow a bend to our model, bent angle. So this earlier model, which models the straight swimmer, is an axisymmetric model. This one is a non-axisymmetric model. And like Direk has explained, I mean, we can actually still break it up, the non-axisymmetric part, into an axisymmetric part, purely non-axisymmetric and active part. Direk has solved for both these two, and this is non-trivial calculation, by the way, and combined that and then found this flow field that he showed in his thing as well. So what I want to point out is that if you consider one particular swimmer, and then if you find the flow around it, you'll see that there is a non-zero circulation. And that circulation actually goes to 0 for phi is equal to 0. Similarly, if you put another swimmer there, the rotation or self-propulsion velocity and the rotational velocity imparted, induced, is very different in these two cases, straight versus that. And we believe that that is affecting the collective dynamics. Direk is actually inspecting that in detail. Okay, so I just want to take 1 or 2 minutes just to summarize this last work, Ambarish's work. He is the other student who is interested to study these swimmers near wall. This is again a non-trivial calculation, mostly because we have to solve the solutions, equations, considering the boundary conditions simultaneously, both on the cell surface as well as on the wall. Okay, it's a non-trivial calculation, but it is done. And as you can see that all these singularities have the modified flow field near a wall. And combining that, I mean, Ambarish already showed this flow field in his talk. Okay, so I'm not going to get into detail. The self-propulsion part also was described in his case. The one thing that was actually I can slightly say a little bit in a modified way is that we saw that this model was actually sufficient in bulk, but there is a shortcoming. The moment we go to a substrate, actually this is not even sufficient. I mean we cannot even use that. So we found that a physical flagella is quite necessary in that case, and introducing a physical flagella, coupling that to the cell body and the substrate is non-trivial again. It's a complex calculation, and it is the result that came out and that described by Ambarish in his talk. That ultimately, if you do that, then you get some physical observation. Okay, and that the same thing was done by Direk. In his case, because of the bend, okay, in the dense suspension, because of the bend, again the coupling gets significantly complex. Okay. And then this is the fresh result from our lab actually. So we are actually calculating this, inspecting the cell-cell interactions now in the crowded environment and the role of flagellar relaxation. Okay, this ends my talk. So in conclusion, I mean, so we talked about the detailed model and the simplified model in these two conditions, crowded environment and the nearest substrate. And I thank my collaborator in ICT, Ravi, and my students, as well as these are my collaborators elsewhere. And these are the funding sources. I'm thankful for that. And thank you for your attention.
Thank you, Tapan. Thanks for a nice talk. So yes, questions, Vibhu?
Yeah, hi Tapan. Hi, nice talk.
Yeah, thank you.
So I have again a couple of questions regarding this the flagellar. When you do the simulation for this flagella, you kind of, correct me if I'm wrong. I mean, so the clockwise and the anti-clockwise rotations seems to have a different torque and speed correlations. If I recollect all those reported literatures.
Right.
Now, you also take care that kind of stops in your kind of when you do these calculations.
Right. So as I said, I mean, can you still see my slides here?
Yes.
Oh, yes, I can say again. Yes.
Yeah. So I mean, usually when the motor is counterclockwise, the stable form is blue. That you have seen in my movie, and when the rotational sense is reversed, then you get these shape changes. So all these shape changes happens actually during the tumbling events, and that is taken care of. I mean, so that is because of the reversal of the motor.
Okay. So and my next question is regarding this image problem. I think it's very interesting. So when you consider this image problem in electrostatics, you have an equipotential surface. I mean, where but here you have a kind of flow field.
Right.
Now, I still didn't understand, I mean, about the correlations and the analogy, because I presume that, then there's a question of geometry as well as, when you talk about the analogy of the charge. Then
this is purely a mathematical mapping. Okay, there is no physics that you can actually map into, but this is purely a mathematical mapping. The mapping comes because of the very similarity of these two differential equations.
Okay.
And maybe you still can see that, okay, there is one term missing from the other equation, but the analogy will come when you look at the green function solution of both these two equations.
Okay.
The green functions are both 1 over r in both the equations. In this case, it's 1 over r times some tensor.
Okay.
We forget about that tensor, but other than that is actually 1 over r. Then this general solution, the integral solutions are very similar. And then there is the one-to-one mapping. So a point charge here maps to a point force there.
Right.
The potential here maps to the flow field there, and so on.
Okay. I got it. Okay. Yeah. Thanks. Yeah. Thanks, Nitin. I'm done.
Yeah, so maybe Tapan, I can ask one question. So in the very beginning, when you just introduced the model, like with the flagella, twist and R and all, so if I understood correctly, so all the activity that you are putting in is into the flagella.
Activity is going into the motor.
I see.
So we rotate the motor. Basically, we apply a motor torque.
Okay. And the motor is sitting inside the cell body.
Motor is sitting inside the cell body, and there is a hook, by the way. So we also model it very nicely, because the hook, the length scale of the hook is very different from the length scale of the flagella. Okay. So if you want, there is a hook. It's a very flexible joint.
Okay.
And this is very important to simulate it very correctly, but you cannot simulate everything together, because length scale are very different. I mean, if you want to simulate it in detail, then simulating the flagella will be very, very slow. Okay, so we generated an effective model for that, and we have everything actually: the hook dynamic, hook elasticity, motor, aerodynamics, everything. Yeah.
So, but as far as I understand, like these flagella are basically microtubules bundles, which are activated using Diane motors, and motors are like distributed everywhere along the length of the flagella.
No. See, you are right. I mean, so some flagella are like this, like the sperm flagella are like that.
Okay.
But for bacterial flagella, I mean, there for at least like E. coli like bacterial flagella, these are passive. Okay. So these are flagellin molecules. These are not microtubule, but flagellin. Okay.
I see. Okay. I didn't know that.
Along the.
But I'm just saying, like, if that were the case, then you probably have to change your model, like, because the activity point is everywhere along the length of the flagellum.
Right. So, and there are works in that line by Zulitzer group. I mean, it's a Dresden work. I mean,
okay.
That happens, for example, in case of the Puller that I showed, the LZ. So, I mean, that happens in that case.
Okay.
Right.
Okay, so if there are no more questions, let's thank Dr. Tapan for this very nice talk. And that brings us to the end of this session. And I think Dr. Denny will take over. I think we'll move into breakout rooms, if I'm not wrong.
That's right. We have 15 more minutes of interactions. Sunita, do you want to say something? Or
Yeah, thank you, Nitin, and all the 4 speakers of the previous session. As Danny said that we can move out to the breakout rooms for independent and more informal interactions. Whatever the leftover questions were there, we can take it into the breakout rooms.
So I have a question. How do you move to the breakout room?
Teleported.
Sorry?
You will figure out.
So on the bottom there is this breakout room, right? So Danny,
You open it.
So now,
Now I can see. Now I can see. Yeah.
Okay, so there are for all the 4 speakers, there are independent rooms.
Yeah.